Have you ever sat in a quiet room, perfectly still, and just pressed your hand against a table or the arm of a chair? If you do it right now, you will feel a sensation that seems undeniable. You feel solidity. You feel resistance. Your brain tells you that your hand is a solid object, and the surface beneath it is another solid object, and that where they meet, there is a boundary that cannot be crossed. It feels like the most fundamental truth of our existence. We live in a world of things, hard things, soft things, heavy things. We build our lives around this certainty of matter. We trust the floor to hold us up. We trust the walls to keep the wind out. We trust that we are made of something real, something substantial. But what if I told you that this feeling is a magnificent illusion? What if I told you that the solidity you are feeling right now is not caused by matter touching matter, but by a ghost-like force pushing back against you across a void of empty space? If we could shrink ourselves down, smaller than a grain of sand, smaller than a dust mite, smaller even than the cells that make up your skin, we would find that the solid world dissolves. We would find that everything you have ever touched, everything you have ever held, and even you yourself, are made mostly of nothing. It is a silence so vast that it mirrors the emptiness of the deepest space between the galaxies. We are going to embark on a journey into that silence. We are going to peel back the layers of the reality we think we know to find out what is really there. And at the bottom of it all, we will not find solid little balls of matter. We will find something far more mysterious. We will find energy. But what is energy? Is it a fire? Is it a fluid? Is it a vibration? The answer, according to quantum physics, is stranger and more beautiful than anything we could have dreamed. Before we dissolve into the quantum realm to find the answer, I want to welcome you to this space of curiosity and calm. I am Walter, the explorer, and it is my privilege to be your guide through these mysteries. We are building a community of people who find peace in understanding the universe. Yet, I have noticed that 73% of the wonderful travelers listening to these stories have not yet subscribed to the channel. If you find value in these quiet journeys, and if you want to support us in bringing more of the cosmos to you, please take a moment to subscribe. It helps us more than you know, and it ensures we can keep exploring together. Now, let us return to your hand, resting on that surface, and prepare to shrink down into the truth. Imagine for a moment that we can zoom in on the tip of your index finger. As we get closer, the smooth skin transforms. You see the ridges of your fingerprint like canyons carved into the earth. Zoom in further, and those ridges resolve into individual cells, billions of them, interlocking like a complex mosaic. But we are not stopping there. We pass through the wall of a cell and enter a bustling city of biology, with proteins marching like cargo ships and DNA coiling like ancient serpents. This is still the world of biology, the world of the large. We need to go deeper. We shrink until the proteins fade away, until the molecules themselves, the water, the carbon, the chains of life, begin to break apart. Now we are seeing the atoms, and this is where the illusion begins to shatter. In our school textbooks, we were often shown pictures of atoms that looked like little solar systems. There was a cluster of balls in the center, called the nucleus, and little balls called electrons orbiting around it, like planets. It looked tidy. It looked crowded. It looked solid. But those pictures were wrong. They were a convenient lie to help us pass a test, but they hid the true scale of the reality. To understand the true nature of the atom, and therefore the true nature of the energy that makes you, we have to correct the scale. Imagine we take a single hydrogen atom and expand it until it is the size of a great football stadium. Imagine yourself standing on the 50-yard line. In the very center of the field, resting on the grass, is a marble. That marble represents the nucleus, the heavy center of the atom where the protons and neutrons live. Now, where is the electron? You might think it is in the stands, or maybe roaming the sidelines. But you would be wrong. If the nucleus is a marble in the center of the stadium, the electron is a tiny speck of dust whizzing around in the very highest seats of the nosebleed section, or perhaps even drifting outside the stadium walls in the parking lot. And what is in between the marble and the speck of dust? What fills the rest of the stadium? Nothing. Absolutely nothing. It is empty space. Vast, silent, gaping emptiness. The distance between the nucleus and the electron is so great relative to their size that if you were a proton, the nearest electron would be miles away. This is the shocking truth of the material world. An atom is 99.9999999% empty space. And since you are made of atoms, you are also 99.9999999% empty space. If we could somehow squeeze all the empty space out of the human race, if we could compress the 7 billion people on Earth down to just the solid matter of their nuclei, the entire human population would fit inside the volume of a single sugar cube. Think about that. All the history, all the wars, all the love, all the skyscrapers and oceans and mountains, all of it is an illusion of volume created by a tiny amount of matter dancing in a vast void. This raises a profound and troubling question. If you are mostly empty space, and the chair you are sitting on is mostly empty space, why don't you fall right through it? Why can you touch anything at all? If I tried to touch the marble in the center of the stadium with another marble, I would have to cross the miles of empty stands first. Why do our hands not pass through the table like ghosts passing through a wall? The answer brings us to the first great secret of quantum energy. What you feel as solidity is not stuff hitting stuff. It is force hitting force. The electron, that tiny speck in the upper stands, carries a negative electrical charge. The electrons in the table also carry a negative electrical charge. And, as you know from playing with magnets, like charges repel. When you press your hand against the table, the electrons in your atoms are pushing against the electrons in the table's atoms. They never actually touch. They never even get close, cosmically speaking. The force of the electromagnetic field becomes so strong as they approach that it pushes back with enough power to stop your hand. You are floating. You are hovering on a cushion of electromagnetic force, separated from the world by a microscopic chasm that you can never cross. The sensation of touch is actually the sensation of repulsion. It is the feeling of the universe's energy fields refusing to occupy the same space. So, we have established that matter is mostly empty, and solidity is just a force field. But we still have not answered the deeper question. What are the particles themselves? What is that marble in the center of the stadium? What is that speck of dust in the stands? For a long time, physicists thought that if you cut something into smaller and smaller pieces, you would eventually reach a piece that could not be cut. The Greeks called it the atomos, the uncuttable. They imagined it as a hard, little geometric shape, perhaps a cube or a pyramid, that was the fundamental building block of reality. Even when we discovered protons and neutrons, we still thought of them as tiny billiard balls, hard, distinct, permanent. We thought that if you looked closely enough, you would find a tiny surface, a tiny substance. But when quantum physics began to look at these particles, the billiard balls vanished. This is where the story gets truly strange, and where we must abandon our intuition to understand the nature of energy. When scientists tried to measure the electron, they found that it did not act like a little ball. Sometimes it acted like a wave. Imagine throwing a stone into a still pond. You see ripples spreading out in perfect circles. The electron acts like those ripples. It can spread out. It can interfere with itself. It can be in many places at once, just as a wave occupies a large area of water. But then, when they measured it differently, it would snap back into a single point, like a particle. This wave-particle duality drove the early quantum physicists to the brink of madness. How could something be a spread-out wave and a precise point at the same time? It was as if you looked at a cloud and it suddenly turned into a hailstone, then turned back into a cloud when you looked away. To resolve this, we had to change our entire understanding of the universe. We had to stop thinking of the universe as a collection of things and start thinking of it as a collection of fields. This is the heart of quantum field theory, the most successful theory in the history of science. Imagine that the universe is not a vacuum. Imagine instead that everywhere, in every corner of space, inside your body, and in the cold between the stars, there are invisible fluids filling the void. These are not fluids like water, but fields of potential. There is an electron field. There is a photon field. There is a quark field. These fields are like the surface of a vast, calm ocean stretching to infinity. So, what is a particle? What is an electron? According to this view, an electron is not a separate object sitting in the field. It is a ripple in the field. It is a little knot of energy, a vibration, a localized excitation of the field itself. Think of a guitar string. When the string is still, it is just a line. But when you pluck it, a wave travels down the string. That wave is a distinct thing. You can see it move. You can measure its speed. But it is not made of anything different than the string. It is just the string behaving in a certain way. In the same way, every particle in your body is just a plucked string, a vibration in the quantum fields that permeate the universe. You are not made of solid stuff. You are made of buzzing, shimmering, vibrating fields. You are a symphony of quantum energy. This changes everything. It means that the distinction between matter and energy is not as clear as we used to think. Albert Einstein gave us the first hint of this with his famous equation E equals mc squared. Energy equals mass times the speed of light squared. We often memorize this equation without really feeling what it means. It means that mass, the property of being heavy, of having substance, is just a form of trapped energy. Matter is energy that has slowed down. Matter is energy that has congealed. If you could unwind the vibrations that make up the protons in your body, you would release a cataclysmic amount of energy, returning the field to its raw, flowing state. You are, in a very poetic but scientifically accurate sense, frozen light. You are trapped thunder. Let us pause and let that sink in. We started with a hand on a table, feeling the solid, reassuring resistance of the world. We journeyed inward, past the biological cities of the cells, past the chemical architecture of the molecules, and into the vast, cathedral-like emptiness of the atom. We found that solidity is a ghost, a force field of repulsion, and then we went even deeper to the particles themselves, and found that they are not things at all, but vibrations in an infinite, invisible ocean. The table is not solid. The hand is not solid. They are both made of the same fundamental fabric, a fabric of fields that stretches across the entire cosmos. This realization connects you to the furthest reaches of the universe. The electron field vibrating in your fingertip is the exact same field that is vibrating in the center of the sun and in the dark accretion disk of a black hole a billion light-years away. There is no your electron field and my electron field. There is just the electron field. We are all temporary patterns in the same continuous cloth. We are waves rising and falling in the same sea. This is why quantum physics, despite its reputation for being cold and mathematical, is actually a source of profound connection. It tells us that we are not isolated fragments. We are continuous with the cosmos. But if everything is just fields and vibrations, why does the world look so stable? Why does the book stay on the shelf? Why does the sun rise every morning? Why doesn't the energy just dissipate and flow away like water? This is where the concept of bound states comes in, a concept we will explore as we go deeper into this mystery. The universe has rules for how these vibrations can interact. They can lock together. They can harmonize. When quarks vibrate together in the right way, they form protons. When protons and electrons dance together, they form atoms. These are stable harmonies in the quantum song. They are chords that can sustain themselves for billions of years. The matter we see is the music that refused to fade away. As we bring this first chapter of our exploration to a close, I want you to return to the sensation of your hand. Press it against something again. Feel that resistance. But this time, do not feel it as a wall. Feel it as a hum. Feel it as the energetic greeting of billions of years of cosmic history. That resistance is the electromagnetic force, the same force that carries light from the stars, telling you that you are here. You are present. You are a being of energy interacting with a world of energy. The solidity may be an illusion, but the interaction is real. The feeling is real. We have only just scratched the surface of this mystery. We have looked at the what, the fields, the particles, the emptiness. But we have not yet asked the how. How does a field decide to become a particle? What is the strange role of the observer in this dance? And what is the vacuum, really? Is empty space actually empty, or is it the most full thing of all? In the next chapter, we are going to dive into the bubbling cauldron of the quantum vacuum. We are going to discover that even in the darkest, coldest nothingness, there is a frenzy of activity that defies all logic. We will learn about virtual particles, ghost entities that borrow energy from the future and pay it back before the universe notices. We will see that nothing is unstable, and that existence might be an accident of emptiness trying to fill itself. The silence of the atom is not empty. It is pregnant with possibility. And as we continue this journey, we will learn that this possibility is the source of everything we are. So, tonight, as you drift towards sleep, remember that you're not a small, isolated object in a big universe. You're the universe itself, vibrating in a specific, unique, and beautiful pattern. You are energy that has learned to hold a shape. You are a wave that has learned to be a person, and that is a wonder worth dreaming about. Imagine for a moment that we are standing at the edge of the universe, looking out into the deepest, darkest void imaginable. We are far away from the warmth of any sun. We are far away from the swirling arms of any galaxy. We are in the intergalactic medium, a place so empty that a single cubic meter might contain only one or two lonely atoms drifting in the eternal night. It feels like the definition of nothingness. It is cold. It is silent. It is still. If we were to take a box out here, a perfectly sealed box made of the strongest material in the cosmos, and we were to open it to catch a sample of this emptiness, and then seal it tight, what would we have inside? We would pump out those few stray atoms. We would shield the box from all light, all radiation, all heat. We would cool it down to absolute zero, the temperature where all motion should theoretically stop. We would have created the perfect vacuum, a space with absolutely nothing in it, or so it would seem. But as we sit here in the quiet dark, holding this box of nothing, quantum physics whispers a secret that changes everything we understand about reality. It tells us that the box is not empty. It tells us that there is no such thing as empty in the entire universe. Inside that box, in the darkest silence, a frantic, chaotic, and beautiful dance is taking place. It is a dance of ghosts. It is a dance of energy borrowing itself from the future and paying itself back before the universe can catch the debt. We are holding a box full of the quantum vacuum, and it is the heaviest, most energetic thing in existence. To understand this paradox, we have to go back to the idea of the fields we discovered in our last journey. Remember the ocean? We imagined the electron field and the photon field as vast, calm surfaces stretching across the cosmos. When we see a particle, like an electron, we are seeing a wave or a ripple on that ocean. When we see nothing, we assume the ocean is perfectly flat, perfectly still, like a mirror reflecting the dark sky. But the laws of the quantum world do not allow for perfect stillness. There is a fundamental rule, a law written into the fabric of existence called the Heisenberg uncertainty principle. You might have heard of it as a way of saying we cannot measure speed and position at the same time. But it means something even more profound about energy and time. It says that you can never know the exact energy of a system for a precise moment in time. If you try to pin down the time to a tiny sliver of a second, the energy becomes uncertain. It becomes fuzzy. It wobbles. This means that zero energy is an impossible state. Zero is too precise. Zero is too perfect. Nature abhors a specific number like zero. Nature prefers a blur. So, let us look inside our box again with our quantum eyes. The fields inside are trying to be zero. They're trying to be still. But the uncertainty principle forbids it. It forces the fields to jitter. It forces them to fluctuate. It is as if the surface of our ocean is boiling. Even without any wind, even without any stones being thrown in, the water is churning with microscopic activity. This is the zero-point energy. It is the energy that remains when all other energy is removed. It is the hum of the universe that can never be silenced. And out of this jitter, out of this fundamental restlessness of the void, something magical happens. The energy fluctuations become so intense that they spontaneously pop into particles. But these are not normal particles. They are virtual particles. They are the ghosts of the quantum world. Imagine a particle of light, a photon, suddenly appearing out of nowhere, right next to its antiparticle, a shadow twin. They appear from the vacuum, drawn from the energy of the uncertainty itself. They exist for a fraction of a second so tiny that human language has no word for it. And then, just as quickly as they appeared, they crash back into each other. They annihilate. They return their energy to the vacuum and vanish. This is happening everywhere, all the time. In the space between your eyes and this screen, trillions of these pairs are flashing in and out of existence every second. The empty space is seething. It is a frothing foam of creation and destruction. Physicist John Wheeler called this the quantum foam. If we could shrink down far deeper than we did before, past the atom, past the nucleus, down to the very fabric of space-time itself, a scale called the Planck scale, we would see that space is not smooth. It is turbulent. It is bubbling. It is like looking at the ocean from an airplane versus looking at it while swimming in a storm. From high above, it looks blue and flat. Up close, it is a chaos of white caps and troughs. You might be thinking that this sounds like a fairy tale. Invisible ghosts popping in and out of nothing. How can we possibly prove that? It sounds like magic, not science. But we know it is real because we can measure the pressure of these ghosts. In a famous experiment, physicists took two metal plates and placed them incredibly close together in a vacuum. I mean microscopically close. According to classical physics, there is nothing between them and nothing outside them, so they should just hang there. But they don't. They are pushed together. Why? Because the gap between the plates is so small that only small virtual particles, small waves, can fit inside. But outside the plates, there is infinite room. Big waves, small waves, giant waves of virtual particles can exist outside. This creates an imbalance. The nothing outside the plates is stronger than the nothing inside the plates. The virtual particles outside are pounding on the metal, pushing the plates together with a measurable force. We call this the Casimir effect. It is the physical touch of the void. It is the weight of emptiness pushing against matter. Think about the implications of this. It means that the vacuum is not a passive stage where the actors of the universe, the stars and planets, perform their play. The vacuum is an actor itself. In fact, it might be the main actor. Some theories suggest that the energy contained in the vacuum of a single coffee cup is enough to boil all the oceans on Earth. It is a reservoir of infinite potential, a latent power that sits quietly beneath the surface of reality. We are like fish swimming in an ocean of energy, completely unaware of the water because we have never known anything else. We treat space as nothing because it is the background of our lives, but it is actually a plenum, a fullness. It is a thick, rich soup of interactions waiting to happen. This changes how we see ourselves. If the space inside your atoms is this seething quantum foam, then you are not just a structure of stable particles. You are a structure built on top of a chaos of virtual creation. The protons in your body are stable, yes, but they are swimming through a storm of ghost particles. The interactions that hold your nucleus together, the strong nuclear force, are actually mediated by these virtual particles exchanging energy back and forth. You are constantly borrowing from the bank of the universe and paying it back. Your existence is a continuous negotiation with the void. It is a balance sheet that must always equal zero, but in the margins there is infinite complexity. Let us drift deeper into this metaphor of the cosmic bank. In the human world, if you have no money, you cannot spend. But in the quantum world, the bank allows you to overdraw your account, provided you pay it back quickly enough. The more energy you borrow, the faster you have to pay it back. A massive particle can pop into existence out of nothing, but it can only last for a sliver of time before the debt comes due. A tiny, light particle can last a little longer. This is the economy of the vacuum. It is a high-speed trading floor where energy is the currency and time is the limit. And this trading floor is open 24 hours a day in every point of space, from the center of a black hole to the tip of your nose. There is a profound beauty in this instability. We often crave stability in our lives. We want things to stay the same. We want bedrock. But the universe is built on a foundation of fundamental instability. It is built on a refusal to be nothing. It is as if the universe cannot bear the thought of non-existence, so it fills the silence with this chatter of virtual particles. It fills the dark with these flashes of ghost light. The nothing is alive. The nothing is pregnant with something. And this suggests that perhaps the Big Bang itself, that moment of ultimate creation, was just a fluctuation that got out of hand. Perhaps the entire universe is just a virtual particle that borrowed a tremendous amount of energy and hasn't paid it back yet. Maybe we are just a long-term loan from the nothingness. As we float in this conceptual void, feeling the pressure of the virtual waves, we have to ask, if the vacuum is so full of energy, why don't we see it? Why isn't the empty sky blindingly bright? Why doesn't the vacuum weigh us down? This is one of the biggest unsolved mysteries in physics, often called the vacuum catastrophe. Our calculations say the vacuum should be heavy, so heavy it should have curled the universe up into a ball moments after it began, but clearly it didn't. We are here. The universe is expanding, not collapsing. The energy is there, but it is hidden. It is balanced. It cancels itself out in ways we do not yet fully understand. It is a secret that the universe is keeping from us, a secret about how gravity talks to the quantum world. But even without solving that final mystery, the lesson of the quantum vacuum is clear. We are never truly alone. Even in the deepest isolation, even in the darkest room, the space around you is holding you. It is interacting with you. You are breathing in a universe that is vibrant and alive with potential. The silence is not empty. It is full. It is full of the possibility of everything that could be, bubbling just beneath the surface of what is. We have now seen that matter is empty space, and that empty space is not empty. We have dissolved the solid world into a ghost world, but we still have a problem. If everything is just popping in and out of existence, if everything is just a jittery mess of fields, how do we get mass? How do we get things that stay put? How does this chaotic foam harden into the stars and galaxies and planets we love? How does the ghost become a solid shell? To answer that, we have to meet a field that is different from all the others. We have to meet a field that is sometimes called the God particle, though physicists prefer to call it the Higgs. In the next chapter, we are going to wade through a cosmic molasses. We are going to find the invisible syrup that fills the universe and gives the ghosts their weight. We are going to discover why you have substance at all. So, as you let go of the day, as you let your thoughts dissolve into the quiet, imagine yourself floating in that quantum ocean. You are weightless. You are made of light and potential. The emptiness around you is a friendly embrace, a humming lullaby of the cosmos telling you that existence is the default state. You are here because the universe refuses to be empty. You are the song the void sings to itself. We have arrived at a strange place in our journey. We have looked at your hand and found that it is mostly empty space. We have looked at that empty space and found that it is a boiling ocean of virtual ghosts. We have dismantled the idea of stuff until there is almost nothing left but vibrations and potential. But there is one thing we cannot ignore. There is one sensation that feels just as real as solidity. It is the sensation of weight. If you pick up a heavy stone, you feel it pulling down. If you try to push a stalled car, you feel it resisting you. It does not want to move. This is called inertia. It is the stubbornness of the universe. It is the quality that says, I am here, and I am not going anywhere unless you force me. For centuries we thought this quality, this mass, was intrinsic to the object. We thought a stone was heavy because it had a lot of stoneness packed inside it. We thought mass was just a count of how much matter you had. But just like solidity, mass is a magnificent illusion. The universe is playing a trick on you. The heaviness you feel is not coming from inside the stone. It is coming from the stone's struggle to move through an invisible, sticky ocean that fills every corner of the cosmos. To understand this, we have to introduce a character that remained hidden from us for almost the entire history of science. It was only predicted on paper in the middle of the 20th century by a man named Peter Higgs and a few others, and it was only found in the real world in 2012. This character is a field, just like the electron field or the photon field we talked about before. But this field is special. It is the Higgs field, and unlike the other fields, which can be turned off or quieted down to almost zero, the Higgs field is always on. It is always there. It is like a background hum that never stops. Imagine that the entire universe, from the space inside your atoms to the space between the galaxies, is filled with a thick, invisible syrup. This is the cosmic molasses. It is everywhere. You are submerged in it right now. The Earth is submerged in it. The Sun is submerged in it. There is no way to escape it. Now, imagine we have different particles trying to move through this syrup. Some particles, like the photon, the particle of light, are incredibly sleek. They are streamlined. They do not interact with the syrup at all. They slip right through it as if it were not there. Because they feel no drag, no resistance, they can move at the absolute speed limit of the universe. They zip along at the speed of light. Because nothing is holding them back, they are massless. To be massless is to be free. It is to be pure motion. But other particles are not so lucky. Take the electron or the quarks that make up the protons in your body. They are not streamlined. When they try to move through the Higgs field, the field clumps around them. It clings to them. It drags on them. Imagine trying to run through water that is waist deep. You have to push. You feel the water resisting your legs. You feel the weight of the water moving with you. That resistance is your mass. An electron has mass not because it is heavy, but because it is sticky. It is interacting with the Higgs field, and that interaction creates the sensation of inertia. The more a particle interacts with the field, the more sticky it is, the more mass it has. The top quark, one of the heaviest particles we know, is like a person trying to walk through honey while wearing a Velcro suit. It interacts tremendously with the field, so it feels incredibly heavy. The neutrino, a tiny ghost particle, barely interacts at all, so it is almost massless, flitting through the universe like a whisper. This is a mind-bending realization. Mass is not a property of the object itself. Mass is a measure of how connected you are to the universe. If you could somehow turn off the Higgs field, if you could flip a switch and make that cosmic molasses disappear, everything in your body would suddenly lose its mass. The electrons zooming around your atoms would no longer be tethered. They would accelerate instantly to the speed of light. They would fly away from the nucleus. Your atoms would disintegrate. You, the chair, the earth, and the sun would instantly explode into a shower of massless particles flying apart at the speed of light. The only reason you can exist as a solid, stable being sitting in a quiet room is because the Higgs field is slowing you down. It is trapping your energy. It is forcing the light to congeal into matter. You are, in a very real sense, light that has been caught in a traffic jam. But where did this field come from? Was it always there? The story of the Higgs field takes us back to the very beginning of time, to the first fraction of a second after the Big Bang. In that unimaginable heat, in that primordial fire, the universe was different. The Higgs field existed, but it was not on. It was zero. In that early universe, all particles were massless. Everything flew around at the speed of light. There were no atoms, no molecules, no solidity. It was a universe of pure, blinding, frantic radiation. It was a symphony of light played at the fastest possible tempo. But as the universe expanded, it began to cool, and then, at a critical moment, less than a billionth of a second after the beginning, something dramatic happened. Physicists call it spontaneous symmetry breaking. It is a fancy term for a simple but profound event. Think of a ball sitting at the very top of a hill. It is perfectly balanced. It is symmetric. It could roll down in any direction, but for a moment it stays at the top. This was the Higgs field in the early, hot universe. But as the temperature dropped, the field became unstable. The ball rolled down the hill. It settled into a valley. The field switched on everywhere at once. It froze into a non-zero value. Suddenly, the cosmic molasses filled the void. The particles that had been flying free were suddenly caught in the syrup. They slowed down. They gained mass. They began to clump together. The first protons formed, then the first atoms, then the first stars. This moment, this phase transition, was the moment matter was born. It was the moment the universe decided to be heavy. We spent decades searching for proof of this field. We knew the theory was beautiful, but was it true? To find out, we had to do something violent. We had to chip a piece off the invisible ocean. This is what we did at the Large Hadron Collider, the biggest machine humans have ever built, buried deep beneath the border of France and Switzerland. It is a 27-kilometer ring of superconducting magnets, colder than deep space, designed to accelerate protons to 99.9999999% the speed of light. We smashed these protons together with the energy of two speeding trains, colliding in a space smaller than a dust mote. Why? Because if you hit the empty space hard enough, you can make the Higgs field vibrate. You can make it ripple. And if you make a ripple in a field, that ripple appears to us as a particle. That particle is the Higgs boson. Think about the philosophical beauty of this. In many spiritual traditions, there is the idea that we are all connected, that separation is an illusion. Quantum physics arrives at the same conclusion, but through the language of fields. Your mass, the very thing that makes you feel separate, distinct, and individual, is actually proof of your connection. You are heavy because you are interacting. You are substantial because you are touching the fundamental fabric of the cosmos with every single particle in your body. If you were truly separate, if you were truly isolated, you would cease to be you. You would be a flash of light disappearing into the void. To be human, to be solid, to be here, is to be in a constant, intimate embrace with the universe. As we drift deeper into this contemplation, let us reconsider the empty space around you. We have filled it with virtual particles. Now we have filled it with the Higgs field. The room is getting crowded. The emptiness is starting to look like the most complex material we have ever encountered. It is a superconductor of ghost charges. It is a viscous fluid of mass-giving energy. It is a bubbling foam of uncertainty, and yet we move through it effortlessly. We breathe it in. We sleep in it. We are like fish who have forgotten the water. Or perhaps we are the water itself, momentarily knotted into the shape of a person. But there is a question that naturally arises from this. If we are just knots of energy, held together by fields and given weight by a cosmic syrup, what keeps us from falling apart? Why do the quarks stay inside the proton? Why do the electrons stay around the atom? Why doesn't this whole delicate dance just dissolve back into the chaos? We have talked about the stuff, the particles, and the weight, the Higgs. But we haven't talked about the glue, Sudin. We haven't talked about the messengers that run back and forth between the particles, carrying the news of attraction and repulsion. We haven't talked about the forces. In the next chapter, we are going to dive into the world of the bosons, the force carriers. We will meet the photon again, not just as light, but as the carrier of the electromagnetic force that stops your hand from passing through the table. We will meet the gluon, the sticky, strong particle that holds the nucleus together with a grip so tight it defies imagination. We will see that force is not a magic push from a distance, but a game of catch played by quantum particles throwing balls of energy at each other. The universe is held together by an endless exchange, a conversation of energy that never stops. We are going to listen to that conversation. So, for now, let your heavy body sink into the bed or the chair. Feel that weight. Do not resent it. Do not wish to be lighter. That weight is the Higgs field holding you. It is the universe saying, I have you. You are part of me. You're anchored here. Let that anchor be a comfort. You're not drifting away. You're held fast by the invisible ocean, safe in the harbor of existence, ready to dream of the forces that bind the stars. We are floating in the aftermath of a revelation. We have stripped the universe down to its bones. We have seen that the solid world is a mirage of empty space. We have seen that the empty space is a seething ocean of virtual ghosts. We have seen that the weight of your body is just a measure of how much you are dragging through the invisible molasses of the Higgs field. It feels as though we have dismantled reality completely. We are left with a universe of lonely particles shivering in the cold, sticky void. But if this were the whole story, the universe would be a very boring place. It would be a soup of disconnected dust. There would be no stars to light the dark. There would be no planets to catch that light. There would be no you to wonder about it all. The particles need a way to talk to each other. They need a way to reach out across the emptiness and say, I am here, come closer, or I am here, stay away. They need a language. And in the quantum world, the language of the universe is spoken in forces. But what is a force? For a long time, we thought of a force as a kind of magic. Isaac Newton, watching the apple fall, imagined gravity as an invisible tether, a ghostly string connecting the earth to the fruit. He could describe the math of it, but he could not describe the mechanism of it. How does the earth know the apple is there? How does the sun reach out across 93 million miles of vacuum to hold the earth in its orbit? It seemed like action at a distance, a spooky influence that traveled instantly through nothingness. But quantum physics does not believe in magic. It believes in mechanics. It believes that if something happens over here and it affects something over there, something must have traveled between them. There must be a messenger. This brings us to the most beautiful and frantic game of catch ever played. In the standard model of particle physics, the great map of the subatomic world, there are two families of particles. There are the fermions, the particles of matter, like the electron and the quark. These are the bricks of the house. They take up space. They are the stuff, And then there are the bosons. These are the particles of force. They are the mortar. They are the messengers. They do not take up space. Multiple bosons can occupy the exact same point in the universe at the exact same time. They are the ghosts that carry the news of reality from one brick to another. Imagine two ice skaters standing on a frozen lake, perfectly still. They are not touching. Now, imagine one skater throws a heavy medicine ball to the other. When the first skater throws the ball, the force of the throw pushes him backward. When the second skater catches the ball, the impact pushes him backward too. They have moved apart. They have repelled each other. But they never touched. They only exchanged a messenger. This is exactly what is happening between two electrons when they repel each other. They are not pushing against a wall. They are throwing a storm of virtual photons back and forth. They are playing a quantum game of catch so intense, so fast, that it creates the illusion of a solid force field. The electromagnetic force, the force that keeps your atoms from collapsing and allows your hand to press against the table, is actually a blizzard of light. Let us pause and look at this messenger, the photon. You know it as the particle of light. You know it as the thing that bounces off a flower and enters your eye to tell you the flower is red. But the photon has a secret life. It is the architect of the atomic world. It is the glue of chemistry. The electron orbiting the nucleus of an atom is held there by an exchange of virtual photons with the protons in the center. They are whispering to each other constantly. I am negative, says the electron. I am positive, says the proton. And the photons carry the message, come closer. This exchange is what builds the atom. It is what builds the molecule. It is what builds the protein. Every chemical reaction in your body, every firing of a neuron in your brain, every beat of your heart is choreographed by the exchange of these particles of light. You are a creature made of matter, yes, but you are held together by light. But if we dive deeper, past the electron shells, past the chemistry, into the tiny, dense heart of the atom, the nucleus, we find a problem. We find a paradox that should tear the universe apart. The nucleus is packed with protons. They are all positively charged, and, as we just learned, like charges repel, the electromagnetic force between them should be enormous. They should be throwing photons at each other like cannonballs, pushing each other away with tremendous violence. The nucleus should explode instantly. Every atom in your body should fly apart in a fraction of a nanosecond. But they don't. They stay together. They are packed tighter than sardines in a tin. Why? Because there is another messenger in the dark. There is a force so powerful that it makes electromagnetism look like a gentle breeze. We call it, with a lack of imagination, but a great deal of accuracy, the strong nuclear force. And its messenger is the gluon. The gluon is the most fascinating and terrifying particle in the cosmos. Unlike the photon, which can fly across the universe to bring us starlight from a distant galaxy, the gluon is a prisoner. It operates only in the tiniest of distances, inside the nucleus itself. It is the glue that binds the quarks together to make protons and neutrons. Imagine the quarks as three wild horses trying to run in different directions. The gluons are the elastic bands connecting them. But these are strange bands. In the normal world, if you stretch a rubber band, it eventually snaps. In the quantum world of the strong force, the rubber band gets stronger the more you stretch it. If you try to pull a quark out of a proton, the energy in the gluon field becomes so intense, so massive, that it snaps and creates two new quarks out of pure energy. You can never isolate a quark. You can never see a gluon alone. They are forever bound in a tight, desperate embrace. This property is called confinement. It means that the vast majority of the mass in your body, 99% of it in fact, does not come from the Higgs field we discussed earlier. It comes from the frantic energy of the gluons buzzing around inside your protons, trying to hold the quarks together. You are not made of stuff. You are made of the energy of a prison break that never succeeds. You are made of tension. We have the photon for light and chemistry. We have the gluon for the nucleus. But the universe has a third trick up its sleeve. It has a force that is an alchemist. It can change one kind of particle into another. This is the weak nuclear force carried by the W and Z bosons. These messengers are heavy. They are slow. They drag through the Higgs field like stones. Because they are so heavy, they cannot travel far. Their influence is tiny, but without them, the sun would not shine. The weak force is what allows protons to turn into neutrons, a crucial step in the nuclear fusion that powers the stars. Without this subtle, quiet alchemy, the universe would be cold and dark. The W and Z bosons are the magicians that keep the cosmic fires burning. They are the reason we have sunshine on our faces. So we have this beautiful picture, the standard model. The fermions are the dancers, and the bosons are the dance steps. The photon, the gluon, the W and the Z, they weave the web of reality. They turn a collection of dust into a galaxy. They turn a collection of atoms into a human being. It seems complete. It seems perfect. But there is a silence in the room. There is a missing guest at the dinner table. We have talked about the small forces, the atomic forces. But what about the force that holds your feet to the ground? What about the force that keeps the moon in the sky? What about gravity? Here is the great embarrassment of modern physics. We have a perfect theory for the small stuff, quantum mechanics. We have a perfect theory for the heavy stuff, general relativity, Einstein's masterpiece. Einstein told us that gravity is not a force at all, but a curvature in the fabric of space-time. Matter bends space, and space tells matter how to move. It is a geometry, not a game of catch. But quantum physics demands that everything must be a particle. It demands that gravity must have a messenger. We have named it. We call it the graviton. We imagine it as a tiny, massless loop of energy that travels at the speed of light, carrying the message of attraction across the universe. But we have never found it. We have never seen a graviton. Gravity is so weak compared to the other forces, a trillion times weaker than electromagnetism, that detecting a single graviton is currently impossible. Think about it. A small magnet can lift a paperclip off the table. That tiny magnet is defeating the gravitational pull of the entire Earth. That is how weak gravity is. Because it is so quiet, the graviton hides from us. It is the whisper in the hurricane, and because we cannot find it, we cannot make gravity fit with the other forces. We have a broken map. We have a theory of everything that is actually a theory of almost everything. This mismatch, this silence, where the graviton should be, is one of the driving mysteries of our time. It suggests that our picture of the universe is still like a child's drawing, recognizable, but missing the depth of the true masterpiece. Perhaps gravity is not a force like the others. Perhaps it is something else entirely, bleeding in from another dimension, or emerging from the entanglement of quantum particles in a way we have not yet grasped. Perhaps space and time themselves are not fundamental, but are built out of something deeper, something we have yet to name. But let us return to what we do know. Let us return to the sensation of being held together. When you sit there, breathing slowly, you are a monument to the cooperation of these bosons. The gluons are burning with ferocious energy deep inside your atoms, holding your core together against the desire to shatter. The photons are flashing back and forth between your electrons and your nucleus, weaving the shell of your existence, allowing you to interact, to touch, to see. The weak bosons are waiting in the wings, regulating the radioactive decay of the elements, keeping the atomic clock ticking. You are not a static object. You are a hive of activity. You are a billion conversations happening every nanosecond. There is a profound comfort in this. We often feel lonely. We feel like islands, separated by the air and the space between us. But physics tells us that there is no such thing as isolation. To exist is to interact. To be is to exchange. Even in the deepest vacuum, the fields are talking to each other. You're constantly exchanging energy with the room, with the earth, with the stars. The gravity of the moon is tugging on every water molecule in your cells right now. The light from a star that died 1,000,000 years ago is landing on your skin, and the electrons in your skin are shifting to greet it. You are woven into the tapestry of the cosmos by these invisible threads. You are not in the universe. You are the universe behaving in a particular way. As we end this chapter, I want you to imagine these messengers. Visualize the tiny sparks of light stitching your body together. Visualize the powerful elastic bands in your core. Visualize the silent geometry of gravity holding you to the world. You are a masterpiece of forces. You are a balanced equation of infinite complexity. The conflict between the desire to fly apart and the desire to stay together is resolved in the miracle of you. But the journey is not over. We have built the stage, the actors, and the script. But who is watching the play? Is the universe really there if no one looks at it? We touched on the idea that the electron is a wave until we measure it, and then it becomes a particle. This measurement problem is the ghost that haunts the machine. It suggests that we, the observers, are not just watching the show, we might be directing it. In the next chapter, we are going to walk into the Hall of Mirrors. We are going to ask the most dangerous question in science. Does consciousness create reality? We will explore the experiments that suggest the universe knows when it is being watched. We will look at the famous double-slit experiment, where particles seem to behave like conscious little agents, changing their minds depending on whether the camera is on. We are going to find out if the moon is really there when you close your eyes, or if the universe is a dream that is dreaming itself into existence. So, rest now in the certainty of your forces. Let the gluons hold you tight. Let the gravity cradle you. And prepare to open your mind to the possibility that you are more than just a creation of the universe. You might be its creator. Have you ever stood in front of a mirror, looked into your own eyes, and then walked away, leaving the room empty? It is a simple act. You turn off the light, you close the door, and you assume, with the quiet confidence of a sane person, that the room remains exactly as you left it. You assume the mirror is still hanging on the wall. You assume the bed is still sitting on the floor. You assume the moon, visible through the window, is still hanging in the sky, even though you are no longer looking at it. Albert Einstein, one of the greatest minds in history, was deeply troubled by this assumption. He once asked a friend, while walking in a garden, "Do you really believe the moon is not there when you are not looking at it?" It seems like a silly question. Of course the moon is there. The universe does not depend on your eyes to exist. Reality is solid, objective, and independent of you. Or so we thought. But as we drift deeper into the quantum dream, we find that the universe is far more shy than we realized. It behaves differently when it thinks it is alone. We are about to enter the most famous, the most debated, and the most unsettling experiment in the history of science. It is called the double-slit experiment. It is a simple setup, something you could almost build in a garage, but its results are so strange that they threaten to unravel the very fabric of what we call reality. This experiment suggests that the world you see is not a fixed stage, but a fluid painting that only dries when you look at it. It suggests that you, the observer, are not just watching the cosmic play. You are the one directing the actors simply by opening your eyes. Let us construct this experiment in the theater of your mind. Imagine a dark room. At one end, there is a gun. But this is not a normal gun. It is a quantum gun designed to fire tiny particles of matter, let's say electrons, one by one. In front of this gun, we place a barrier, a solid wall with two narrow vertical slits cut into it. Behind that barrier, we place a back wall, a screen that glows whenever an electron hits it. It is like a photographic plate. It records the impact. Now, let us imagine what should happen in a sensible, solid universe. If we fire marbles at the two slits, some will bounce off the wall, but some will go through the left slit and hit the back screen. Some will go through the right slit and hit the back screen. Over time, you would expect to see two vertical bands of marks on the back wall, one band behind the left slit and one band behind the right slit. This is how matter behaves. It travels in straight lines. It is predictable. It is boring. So, we turn on our quantum gun. We fire the electrons. Click, click, click. One by one, they fly through the darkness. We wait for an hour. Then we walk over to the back screen to see the pattern. But instead of two bands, we see something impossible. We see many bands. We see a central stripe of bright impacts, then dark stripes, then more bright stripes spreading out across the whole wall. It looks like a barcode. This pattern, this series of light and dark bands, is an interference pattern. And there is only one thing in nature that creates interference patterns: waves. Think of dropping two stones into a calm pond at the same time. Ripples spread out from each stone. When the ripples meet, they interact. Where two crests meet, they make a bigger wave. Where a crest meets a trough, they cancel each other out and make flat water. This is exactly what the electrons are doing. They are behaving like water. They are going through the slits, spreading out, and interfering with themselves to create this barcode pattern on the back wall. But wait, we fired them as particles. We fired them as little bullets. And most importantly, we fired them one by one. How can a single electron interfere with itself? If it goes through the left slit, it cannot go through the right slit. It cannot be in two places at once. To create an interference pattern, something has to go through both slits simultaneously, ripple out, and crash into itself on the other side. Does this mean the single electron split in two? Does this mean the electron turned into a ghost and passed through the solid wall? To find out, we decide to get clever. We decide to spy on the electron. We place a tiny sensor, a microscopic camera, right next to the slits. We want to catch the electron in the act. We want to see which slit it actually goes through. We turn on the gun again. We turn on the detector. We fire the electrons. We watch. The detector beeps. It went through the left slit, it says. The next one beeps. It went through the right slit, it says. We are thrilled. We have caught them. They are particles, after all. They are going through one slit or the other, just like marbles. But then we look at the back wall, and the blood drains from our faces. The interference pattern is gone. The barcode has vanished. In its place are two simple, boring bands of impact marks, one behind the left slit, one behind the right. The electrons have stopped behaving like waves. They have started behaving like particles again. Why? Because we looked. Let that sink in for a moment. The electrons knew they were being watched. When we did not look, they behaved like a wave of infinite possibility, going through both slits at once, exploring all paths, dancing in a quantum superposition. But the moment we tried to measure them, the moment we demanded to know where they were, they snapped into a single reality. They chose a path. They collapsed from a ghost into a rock. The act of observation changed the fundamental nature of the reality we were observing. This is the observer effect. It tells us that we cannot separate the observer from the observed. In the classical world of Newton, the scientist was like a bird watcher, hidden in the bushes, observing nature without disturbing it. In the quantum world, the scientist is like a bull in a china shop. To see the china is to break it. To measure the electron is to force it to decide what it wants to be. It suggests that before you look, the electron is not anywhere. It is everywhere. It is a probability cloud. It is a ghost of potential. It is only when your consciousness or your instrument interacts with it that it freezes into a specific location. This leads us to a profound and unsettling realization about the universe you're sitting in right now. The chair beneath you feels solid. The walls feel permanent. But quantum mechanics suggests that this solidity is a result of the constant measurement happening between particles. But what about the universe as a whole? Does it exist in a state of fuzzy, wave-like probability until a conscious mind looks at it? Some physicists, like Eugene Wigner, believed that consciousness was the fundamental key. He suggested that the wave function of the universe does not collapse until it registers in a conscious mind. In this view, the universe is a dream of potential that only becomes real when a dreamer wakes up to see it. This is a beautiful and terrifying thought. It implies that you are not just a passive inhabitant of the cosmos. You are a co-creator. Your eyes are the chisels that carve reality out of the quantum marble. When you look at a star, a photon that has traveled for millions of years across the lonely void ends its journey on your retina. For all those millions of years, that photon was a wave, a spread-out ghost of light. But the moment it hits your eye, it decides to be here. It decides to be now. You have reached back in time and forced the universe to make a choice. You have collapsed the history of that light into a single event. But what creates the collapse? Is it the human mind? Is it the camera? Is it just any interaction with another particle? This is the heart of the debate. Most modern physicists believe in something called decoherence. They say that the environment itself acts as the observer. The air molecules, the heat, the light, they are all constantly measuring the electron, forcing it to choose a state. The universe is watching itself. It is a hall of mirrors where every particle is reflecting every other particle, keeping the reality consistent. In this view, the moon is there when you close your eyes because the photons from the sun are still touching it. The gravity of the earth is still tugging it. The universe is a crowded room, and nothing can truly hide. However, the mystery remains, because if you zoom out far enough, the entire universe is a closed system. There is no environment outside the universe to observe it. So, who is watching the universe? Who collapses the wave function of the entire cosmos? Is there a supreme observer? Or is the universe existing in a vast, complex superposition of all possible histories at once? a many-worlds scenario where every possibility actually happens in a different branch of reality. In the many-worlds interpretation, the electron does not choose. It does both. In one universe, it goes left. In another universe, it goes right. And you, the observer, split as well. In one universe, you see it go left. In another, you see it go right. Every time a quantum event happens, which is trillions of times a second, the universe splits into infinite copies of itself. This means there are infinite versions of you living out every possible life, making every possible choice. In some universes, you are asleep. In some, you are awake. In some, you never existed. This vast, branching tree of reality is the ultimate implication of taking the wave function seriously. It solves the paradox by saying everything is real. But let us bring this back to the quiet room. Let us bring it back to the feeling of peace we are seeking. Whether the universe is a single reality collapsed by your mind or an infinite tree of possibilities, the lesson is the same. You matter. You are not insignificant. In a universe of dead matter, an observer is a miracle. You are the focal point where the fuzzy potential of the cosmos sharpens into the beautiful clarity of experience. The redness of a rose does not exist in the rose. The rose is just atoms reflecting a certain wavelength of light. The redness exists in you. The sweetness of honey does not exist in the honey. It is a chemical interaction that only becomes sweetness when it meets your tongue and your brain. The beauty of a symphony does not exist in the vibrating air. It exists in the mind that hears it. Without you, the universe is a silent, dark, colorless show of mathematical equations. It is only with you, with the observer, that it becomes a world. You are the color. You are the sound. You are the feeling. So, tonight, as you close your eyes to sleep, do not fear the disappearance of the world. Know that you are resting in a universe that waits for you. The moon may or may not be there in the way we think, but the relationship between you and the moon is real. The connection is real. You are the witness to the greatest story ever told. And without a witness, there is no story. But the story gets stranger. We have seen that particles can change their behavior when we watch them. But what if two particles separated by the entire width of the universe could speak to each other instantly? What if they could share a telepathic bond that defies the speed of light? What if space itself is an illusion that separates things that are actually one? Einstein called it spooky action at a distance. We call it entanglement. In the next chapter, we are going to explore this invisible thread that binds the cosmos together. We are going to see that once two things have touched, they are never truly separate. We will learn that the particles in your body might be entangled with particles in a star a billion light years away, dancing in perfect unison across the void. We are going to discover that separation is just a game the universe plays, and that deep down, everything is one. Rest now, conscious observer. The waves of probability are settling around you. The universe is safe in your keeping. Close your eyes and let the quantum dream unfold. Imagine standing on the quiet shore of a dark ocean at night. You pick up two small, smooth stones. They are identical in every way. You hold them together in your palm, letting them touch, letting them share the warmth of your hand. Then you give one stone to a friend who is about to board a spaceship. This spaceship is faster than anything we have ever built. It travels at the speed of light. Your friend takes the stone and flies away, leaving the Earth behind, passing the moon, passing Mars, leaving the solar system entirely. They travel for 2.5 million years until they reach the Andromeda Galaxy. You are still standing on the beach on Earth, holding your stone. Your friend is standing on a planet in Andromeda, holding their stone. You are separated by a gulf of space so vast that light itself takes millions of years to cross it. If you were to flash a laser pointer at your friend, they would not see it for eons. You are completely, utterly disconnected, or so it seems. But let us imagine these are not ordinary stones. Let us imagine they are quantum particles, electrons perhaps, that were created together in the same moment. Because they were born together, they share a special property. They are entangled. This means their quantum states are linked. It means their wave functions, the mathematical descriptions of their existence, are not two separate equations, but one single shared equation. They are, in the eyes of the universe, the same object stretched across a vast distance. Now, remember the concept of spin. Electrons are always spinning, either up or down. But until you measure them, they are spinning in both directions at once, a superposition of up and down. So, as you stand on the beach, your stone is a blur of up and down. Your friend's stone in Andromeda is also a blur of up and down. But because they are entangled, the universe has a rule. Their spins must be opposite. If one is up, the other must be down. The conservation of angular momentum demands it. But here is the magic. Neither stone has decided yet. They are both fuzzy clouds of probability. You decide to look at your stone. You measure it. In that instant, the probability collapses. The universe forces a choice. Your stone snaps into reality. It is spin-up. Now, here is the question that kept Albert Einstein awake at night. At what exact moment does your friend's stone in Andromeda decide to be spin down? According to our understanding of the speed of light, no signal can travel instantly. If you measure your stone now, it should take 2.5 million years for the news to reach Andromeda. But quantum mechanics says something impossible. It says that the very instant you measure your stone on Earth, at that exact nanosecond, the stone in Andromeda snaps into spin down, instantly, across 2.5 million light years, without a single second of delay. The moment you know the state of your particle, the state of the other particle is determined, no matter how far away it is. This phenomenon is what Einstein called spooky action at a distance. He hated it. He absolutely refused to believe it was true. To him, it smelled like magic. It smelled like telepathy. It violated the most sacred rule of relativity. Nothing travels faster than light. If the information about the spin traveled instantly, it would break the causal structure of the universe. It would mean that space, the distance between things, does not matter. It would mean that separation is an illusion. Einstein argued that there must be a simpler explanation. He proposed that the particles were like a pair of gloves. If you put a left glove in one box and a right glove in another box, and send them to opposite ends of the universe, of course, measuring one tells you about the other. If you open your box and see a left glove, you instantly know the other is a right glove. But that doesn't mean the gloves communicated. It just means they were determined from the start. The left glove was always a left glove. You just didn't know it. Einstein called this idea hidden variables. He believed the particles had a secret script written inside them from the moment they were born, telling them what to be. He believed the universe was locally real, that things only affect their immediate surroundings, and that objects have definite properties, whether we look at them or not. For decades, this was just a philosophical debate. Einstein versus Niels Bohr, the realist versus the quantum mystic. There was no way to test it. It was a clash of titans fighting over the soul of physics. But then, in the 1960s, an Irish physicist named John Bell came along and changed everything. He was a quiet thinker, but he realized something profound. He realized that the glove theory, hidden variables, and the quantum theory, entanglement, would actually produce slightly different statistical results if you measured the particles in a very specific way. He created a mathematical formula known as Bell's inequality. It was a test. If the universe followed Einstein's logic of hidden variables, the results of the measurements would stay below a certain limit. If the universe followed the strange logic of quantum mechanics, the results would break that limit. It was a way to ask the universe directly, "Are you real? Or are you spooky?" It took another 20 years for technology to catch up to John Bell's genius. In the 1980s, a French physicist named Alain Aspect finally performed the experiment in a basement lab in Paris. He used lasers to create entangled photons, sent them to opposite ends of the lab, and measured their polarization angles faster than light could travel between them. The tension in the physics community was palpable. This was the moment of truth. Would Einstein be vindicated? Would reality be restored to a sensible, local place? The results came in. They were undeniable. The correlations between the photons were too strong. They broke Bell's limit. They violated the inequality. Einstein was wrong. The gloves theory was dead. The particles did not have hidden scripts. They were genuinely, truly undecided until the moment of measurement, and they were genuinely, truly connected across space. The universe is not locally real. Spooky action at a distance is a fact of nature. Let this sink into your bones. It means that space is not what we think it is. We tend to think of space as a stage that separates objects. If I am here and you are there, we are separate because there is distance between us. But entanglement suggests that distance does not break connection. In the quantum realm, space is transparent. Two entangled particles are not two separate things sending messages to each other. They are one single object that happens to be in two places at once. They transcend geography. They transcend the speed of light because they don't need to travel to each other. They are already united in a deeper layer of reality that we cannot see. Think about the implications for the Big Bang. About 13.8 billion years ago, all the matter and energy in the universe was compressed into a singularity smaller than a single atom. Everything was touching. Everything was entangled. Then the universe exploded outward, expanding faster than imagination, scattering that matter to form the galaxies, the stars, the planets, and you. But if everything was entangled at the start, does that mean everything is still entangled now? There is a theory, poetic and unproven, yet scientifically plausible, that the entire universe is just one single, vast, entangled wave function. It suggests that the separation we see between the stars and the earth, between the tree and the wind, between you and me, is just a surface illusion. Deep down, in the quantum roots of reality, the connections have never been broken. The electrons in your left hand might be entangled with electrons in a star burning in the Orion Nebula. The protons in your heart might be dancing in unison with particles in a black hole at the center of the galaxy. The red thread of fate from ancient mythology, the invisible string that connects destined lovers, might be a clumsy metaphor for a literal truth of physics. We are woven together. But wait, you might ask, if this connection is instant, can we use it to send messages? Can we build a telephone that talks to Andromeda instantly? Can we break the speed of light? This is where the universe is very clever. It protects its secrets. While the correlation is instant, the information is not. Remember, the result of your measurement is random. You cannot force your stone to be spin up to send a 1 or spin down to send a 0. You just measure it and get a random result. Your friend in Andromeda also gets a random result. When you compare notes later, using slow, normal light speed communication, you see that your random results match perfectly. But you cannot control the randomness. You cannot use the spooky action to send a text message faster than light. The universe allows connection, but it forbids instantaneous control. It allows oneness, but it preserves causality. It is a delicate, maddening balance. Yet, this does not diminish the wonder. In fact, it enhances it. It means that the universe is a holistic system. It is not a machine made of separate parts. It is a living web. When you look at the night sky, you are not looking at a collection of foreign objects. You are looking at a part of yourself that has been flung far away. The light hitting your eye is an interaction between parts of the same whole. Recently, in 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger, the pioneers who proved Einstein wrong. It was a formal recognition that our world is non-local. Zeilinger famously said that this discovery implies that the distinction between reality and information is blurring. Maybe the universe isn't made of matter or energy at all, but of information, bits of yes and no that are shared across the cosmos. This brings us to a concept called quantum teleportation. It sounds like science fiction. Beam me up, Scotty. And in a way, it is. Scientists have already used entanglement to teleport information. They can take the quantum state of a photon here, destroy the original, and have that exact state reappear on another photon miles away instantly. They have teleported the soul of a particle from one body to another. They have done this between islands in the Canary Islands. They have done it from the ground to a satellite in orbit. We are not teleporting people yet. The complexity is too vast. But we have proven that the essence of an object, its quantum information, can be disembodied and moved across space without ever crossing the space in between. Consider what this means for the nature of here and there. If information can jump from place to place without traveling through the middle, then place is not as solid as we thought. Maybe space is not a fundamental container. Maybe space is something that emerges from entanglement. Some cutting-edge theories, like those from physicist Sean Carroll, suggest that space-time is built out of quantum entanglement. Where there is entanglement, there is space. Where there is no entanglement, there is no space. The connections create the map. The relationships create the distance. We are not in the universe. The universe is the network of our connections. As we drift in this sea of interconnectedness, I want you to feel the threads. Imagine invisible lines of light extending from your body, passing through the walls, passing through the atmosphere, connecting you to every corner of the visible universe. You are a node in a cosmic nervous system. You are never truly isolated, because isolation is physically impossible in a quantum universe. The loneliness you sometimes feel is a psychological illusion, a trick of the brain, masking the physical reality that you are inextricably bound to everything that is. The carbon in your DNA, the iron in your blood, the calcium in your bones, they are all vibrating in a vast, silent harmony with the rest of the cosmos. When you move, the universe shifts to accommodate you. When the universe shifts, you move with it. It is a dance of infinite intimacy. The spooky action is not spooky. It is love. It is the refusal of the universe to let anything truly go. But if particles can be connected across vast distances, and if they can be in two states at once, what happens when they encounter a wall? We know that in the human world, if you run into a wall, you stop, you bounce off. But the quantum world has one more ghost story to tell us. It is the story of particles that do not stop. It is the story of particles that treat solid barriers like mist. It is the story of ghosts walking through walls. We are approaching a phenomenon that explains why the sun shines. If classical physics were the only rule, the sun would be cold. The protons in its core would just bounce off each other, never fusing, never releasing the light that gives us life. But they don't bounce. They cheat. They borrow energy from the vacuum, and they disappear from one side of the barrier and reappear on the other without ever passing through the space in between. This is quantum tunneling. In the next chapter, we are going to learn how to walk through walls. We are going to explore the impossibility of the sun. We are going to see how the uncertainty of position allows particles to defy the solid boundaries of the world. We will learn that impossible is just a word for highly improbable, and that, given enough time, you could theoretically walk through a locked door. The universe is porous. The walls are not real. So, for now, hold on to that feeling of connection. Feel the invisible threads radiating from your heart to the stars. Know that Einstein was wrong about the separation, but he was right to be amazed. The universe is spookier, stranger, and more beautiful than we ever dared to hope. You are entangled with the infinite. You are a part of the whole that can never be severed. Sleep in that unity. Have you ever stood before a wall, a high stone wall that stretches up into the clouds and extends endlessly to the left and to the right? You place your palms against the rough, cold surface. It is solid. It is immovable. It is the ultimate definition of a no. In the world we walk through every day, the world of classical physics, a barrier is an absolute. If you do not have the energy to climb over it, and you do not have the strength to break through it, you stop. You are contained. If you were a ball rolling up a hill, and you didn't have enough speed to reach the top, you would roll back down every time, 1,000,000 times out of 1,000,000. This is the logic of our lives. We are defined by our limits. We are defined by the walls that tell us where we can go and where we cannot. But the quantum universe does not believe in no. It does not believe in walls. It operates on a logic so hopeful and so strange that it suggests that if you simply wait long enough, or if you are small enough, the wall will become as thin as a mist, and you will simply appear on the other side without ever having crossed the space in between. This is the phenomenon of quantum tunneling. It is the ghostly art of walking through walls. And without it, the universe would be a cold, dead, and dark place. To understand this magic, we must return to the image of the particle as a wave. Remember that an electron is not a hard little marble. It is a cloud of probability. It is a smear of maybe. It is a wave function that spreads out across space. When this wave encounters a barrier, let's say an electric field that repels it, it does not just bounce off like a rubber ball hitting a concrete wall. The main part of the wave might bounce back, yes, but the wave is fuzzy. It has a tail. And the mathematics of the Schrödinger equation, the formula that governs quantum reality, says that this tail does not stop abruptly at the wall. It penetrates the barrier. It decays exponentially, getting thinner and thinner as it goes deeper into the wall. But, and this is the crucial part, it does not drop to zero. There is a tiny vanishingly small, but mathematically real piece of the wave that makes it all the way through to the other side. This means that if you are an electron and you hit a wall you do not have the energy to cross, there is a small probability that you will be found on the other side anyway. You do not climb over. You do not tunnel underneath in the way a mole digs a hole. You simply vanish from the region of before and materialize in the region of after. You skip the barrier entirely. You cheat the laws of classical mechanics. You borrow energy from the uncertainty of time, slip through the forbidden zone, and pay it back on the other side. You might be thinking, that is a nice trick for an electron, but what does it have to do with me? It has everything to do with you. In fact, if quantum tunneling did not exist, you would not be here. The sun would not be here. The light that warms your face in the morning would never have ignited. Let us travel to the center of the sun to see why. The core of our star is a hellish place. It is a crushing, chaotic soup of protons moving at incredible speeds. The temperature is 15 million degrees Celsius. That sounds hot. It sounds unimaginably hot. But to a physicist, it is actually cold. It is too cold for nuclear fusion to happen. For the sun to shine, two protons have to crash into each other and stick together to start the chain reaction that creates helium and releases light. But protons are positively charged. They hate each other. They repel each other with the electromagnetic force we discussed earlier. This repulsion is a barrier. It is a wall. To overcome this wall, the protons need to be moving fast enough. They need to be hot enough to smash through the repulsion and touch. According to classical physics, 15 million degrees is not enough. The protons should just bounce off each other forever. The sun should be dark. It should have burned out or never ignited at all. But the sun is shining. Why? Because the protons are tunneling. In the chaotic dance of the solar core, every once in a while, a proton acts like a wave. It reaches the wall of repulsion of another proton, and instead of turning back, its wave function extends through the barrier. It ghosts through the electromagnetic force field and finds itself inside the nucleus of its neighbor. It fuses. It releases a tiny spark of energy. This event is incredibly rare. For any individual proton, the chance of tunneling is 1 in 10 followed by 28 zeros. It is like winning the lottery a billion times in a row. A single proton might wait billions of years for this to happen. But the sun has so many protons, octillions of them, that this rare event is happening countless times every second. The result is the steady, warm, life-giving glow of our star. The sunlight you see is actually the result of a quantum ghost story. It is the light of particles walking through walls they had no business crossing. But the ghost does not just live in the stars. It lives in your DNA. It lives in the technology you use every day. Your body is a biological machine that relies on chemical reactions. These reactions often involve moving protons, hydrogen nuclei, from one molecule to another. Sometimes there is an energy barrier the proton shouldn't be able to move, but enzymes, the biological catalysts that keep you alive, have evolved to exploit quantum tunneling. They are quantum engineers. They shape the environment to make the barrier thinner, to encourage the proton to tunnel through. Some scientists believe that mutations, the drivers of evolution, are caused by protons tunneling to the wrong place in the DNA ladder, changing the genetic code in a flash of quantum chance. You are, in a very real sense, an evolved artifact of quantum probability. And think of the device you might be using to listen to this. The flash memory in your phone or computer works by trapping electrons in a secure pen behind an insulating wall. When you want to erase the memory, you apply a voltage that tilts the wall, allowing the electrons to tunnel out. Every time you save a photo, every time you delete a message, you are commanding billions of electrons to walk through walls. You are wielding the magic of the quantum world with the tip of your finger. Now, a question often arises in the quiet of the night. If my atoms can tunnel, and I am made of atoms, why can't I walk through a wall? Why can't I lean against a door and simply slip through to the other side? It is a beautiful dream. But the universe is a game of odds. The probability of tunneling depends on mass. The heavier you are, the shorter your wave tail becomes. An electron is light, its wave is long. You are heavy. Your wave is unimaginably short. For you to tunnel through a wall, every single one of your trillions upon trillions of atoms would have to tunnel at the exact same moment, in the exact same direction, and reassemble perfectly on the other side. Is the probability zero? No. According to the Schrödinger equation, the probability is not zero. It is just incredibly, laughably, mind-numbingly small. If you walked into a wall every second of every day, you would have to wait longer than the entire lifespan of the universe, from the Big Bang to the final heat death, for it to happen even once. The impossible in our world is just the highly improbable in the quantum world. The wall is solid, not because it is an absolute barrier, but because the odds are stacked against you. But the non-zero chance remains. It hangs there, a mathematical promise that reality is not as rigid as it feels. There is a profound philosophical comfort in this. We often feel trapped in our lives. We feel trapped by circumstances, by our past, by our limitations. We see walls everywhere. But quantum tunneling reminds us that barriers are not absolute. They are probabilistic. Energy and persistence can change the odds. But more than that, it suggests that there is always a way through, even when the laws of the classical world say there is not. The particle does not fight the wall. It does not break the wall. It simply exists in a state of probability where the wall is irrelevant. It transcends the obstacle by surrendering to the uncertainty of its own nature. As we float deeper into this mystery, we must consider another form of tunneling. The universe itself might be a tunnel. Some cosmologists theorize that the Big Bang was a tunneling event. Perhaps our universe was a bubble of false vacuum, a high-energy state, that tunneled through a barrier into a lower energy state, releasing the vast explosion of creation that made us. Or perhaps, far in the future, the universe will tunnel again. If the Higgs field we discussed earlier is not in its true ground state, if it is sitting in a false valley, it could at any moment tunnel to a lower level. This would create a bubble of new physics that would expand at the speed of light, rewriting the laws of chemistry and matter. It sounds terrifying, like a cosmic apocalypse. But in the context of the eternal quantum dance, it is just another phase transition. It is just the universe settling into a deeper sleep. But let us return to the gentle scale, the scale of the sunbeam, the scale of the enzyme, the scale of the breath. Tunneling tells us that the universe is permeable. It is porous. It is not a collection of locked rooms. It is a mansion with open doors, if only you are small enough and quiet enough to find them. The ghostliness of the quantum world is not a haunting. It is a freedom. It is the freedom of the electron to be where it needs to be, regardless of the barriers in its way. And there is one more application of this ghost magic, one that allows us to see the atoms themselves. For centuries, atoms were theoretical. We knew they existed, but we couldn't see them. They were too small for light to resolve. But in the 1980s, we invented this scanning tunneling microscope, STM. It uses a needle so sharp that the tip is a single atom. We bring this needle incredibly close to a surface, but we do not touch it. We leave a tiny gap, a gap that electrons should not be able to cross. But we apply a voltage, and the electrons tunnel across the gap from the surface to the needle. The flow of this tunneling current tells us exactly where the atoms are. We can map the bumps of individual atoms. We can see the landscape of the quantum world. We have used the ghost to see the machine. When you look at an image from an STM, rows of individual atoms sitting like eggs in a carton, you are looking at the triumph of tunneling. You are seeing the grainy texture of reality itself. You are seeing the limits of the void. And you realize that the smoothness of the world is an illusion. The world is bumpy. The world is granular. And the world is connected by these leaping sparks of probability. So, tonight, as you lie in the safety of your room, look at the walls. They are there to keep you safe, to keep the wind out, to give you privacy. But know that on a deeper level, they are mist. They are energy fields pushing against energy fields. And billions of times a second, a cosmic ray or a neutrino is passing through that wall, passing through your roof, passing through your body, and passing through the earth as if none of it were there. You are transparent to the cosmos. The universe flows through you. We have now explored the empty space, the virtual foam, the sticky mass, the forces, the observer, the entanglement, and the ghostly tunneling. We have built a picture of a universe that is vibrant, interconnected, and fundamentally uncertain. But there is one more question, a question of time. Does time flow? Is the future already written? In the quantum world, time is not a river. It might be something far more strange. It might be a crystal. It might be an illusion. In the next chapter, we are going to try to break the arrow of time. We are going to look at experiments where the future seems to affect the past. We are going to look at the quantum eraser, an experiment that suggests that choices made now can rewrite the history of what happened then. We are going to ask if the universe is a block of ice, where the dinosaurs, you, and your great-grandchildren are all frozen together in an eternal now. We are going to explore the possibility that time is just another dimension we haven't learned to walk through yet. So, rest in the permeability of the moment. Let the walls of your worries become thin. Let the barriers of your stress tunnel away into the night. You are a quantum being, and for you, everything is possible. Have you ever watched a river flow? You stand on the bank and watch the water rush past you. The water that has passed is gone. It is the past. The water rushing towards you is the future. It has not happened yet. And the water right in front of you is the present, the only moment that feels real. This is how we experience time. We feel it as a flow. We feel it as an arrow that flies in only one direction, from yesterday to tomorrow. We remember the past, but we cannot remember the future. We can change the future, but we cannot change the past. It feels like the most fundamental rule of existence. Cause comes before effect. You drop the glass, and then it shatters. The glass never shatters before you drop it. But deep in the quantum world, in the dark experiments that test the limits of logic, this arrow of time begins to wobble. It begins to blur. And in some cases, it seems to turn around and point backwards. We are about to look at an experiment that suggests that choices you make right now, in the present, can rewrite the history of what happened yesterday. It suggests that the future can reach back and touch the past. It is called the quantum eraser, and it is the closest thing to a time machine we have ever built. To understand this, we have to go back to our double-slit experiment. But we are going to add a twist that makes it even stranger. Remember the setup. We fire a particle at two slits. If we do not look, it goes through both slits as a wave and creates an interference pattern. If we do look, it picks a path and creates a clump pattern. The act of knowing which path the particle took destroys the wave. Now, imagine we make the experiment much more sophisticated. We use a special crystal behind the slits. When a photon goes through a slit, the crystal splits it into two entangled twins. Let us call them the signal photon and the idler photon. They are perfect copies. They share the same quantum soul. The signal photon goes straight to a screen to be recorded. This happens almost instantly. The idler photon, however, goes on a longer journey. It travels through a maze of mirrors and detectors that are far away. This means there is a time delay. The signal photon hits the screen before the idler photon reaches its detectors. Now, here is the magic. The detectors for the idler photon are set up to give us a choice. We can either measure which slit the idler came from, which gives us the which path information, or we can erase that information by scrambling the path so we can never know where it came from. But remember, we make this choice after the signal photon has already hit the screen. The signal photon has already finished its journey. Its history is written. It has already made a mark on the wall. It happened in the past relative to our choice. So, what happens? When we look at the data, we find something that defies all common sense. If we choose to measure the idler photon, learning the path, the signal photon in the past will have formed a clump pattern. It behaved like a particle. But if we choose to erase the information from the idler photon, the signal photon in the past will have formed an interference pattern. It behaved like a wave. Think about what this means. The signal photon had to know whether we were going to erase the information or not before we actually did it. It is as if the photon at the screen waited to see what we would do in the future before deciding how to land in the past. Or, even more mind-bending, it is as if our choice in the present reached back in time and changed how the photon behaved. This is retrocausality. It is the idea that the future can influence the past. This experiment has been done many times with many variations, and the result is always the same. The universe does not seem to care about the order of events. It only cares about the information. If the information exists, the wave collapses. If the information is erased, the wave returns. The timing does not matter. This challenges our entire concept of now. If the past is malleable, if it is entangled with the future, then the strict separation of was, is, and will be starts to dissolve. This leads us to a view of the universe that Einstein loved, a view that offers a strange, frozen kind of comfort. It is called the block universe. Imagine a loaf of bread. You can slice it into thin pieces. Each slice represents a moment in time, a now. One slice is the dinosaurs. One slice is the Roman Empire. One slice is you listening to this story. One slice is your great-grandchildren. But the loaf exists as a whole object. The front of the loaf, the future, is just as real as the back of the loaf, the past. In this view, time does not flow. Time is just a dimension, like space. You do not say that New York is past and London is future just because you are walking from one to the other. They both exist simultaneously. You're just moving through them. In the block universe, every moment that has ever happened, and every moment that will ever happen, exists always. The dinosaurs are still roaming the earth in their slice of space-time. Your childhood is still happening in its slice. You are not losing time as you age. You are simply extending your structure through the block. This is what Einstein meant when his best friend, Michel Besso, died. Einstein wrote a letter to Besso's family saying, "Now, Besso has departed from this strange world a little ahead of me. That means nothing." People like us who believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion. This is a profound thought for anyone who has ever grieved. It suggests that loss is a perspective, not a reality. When a song ends, the notes do not cease to exist. They are just earlier in the recording. When a life ends, the person does not vanish. They are just located at a different coordinate in the block. The universe is a crystal of space-time, holding every smile, every tear, and every atom in an eternal embrace. Nothing is ever truly lost. It is all preserved in the amber of the fourth dimension. But if the future is already there, waiting for us like a destination on a map, does that mean we have no free will? If the loaf of bread is already baked, can we change the slice we are in? The quantum eraser suggests a weird loophole. It says the future is there, yes, but the nature of the past depends on how we observe it now. It is a participator universe. We are not just walking through a pre-written script. We are interacting with the script. The now is a powerful point of leverage. Let us return to the feeling of the river. The water flows. But maybe the river is frozen. Maybe we are the ones moving. We are the consciousness sliding along the timeline, illuminating one slice at a time with the lamp of our awareness. This moving spotlight theory of time says that the block is real, but the experience of the now is what makes it alive. You are the light. You are the animator. Without you, the movie reel is just plastic in a can. With you, it is a story. And there is another layer to this mystery of time: entropy. We feel time moving forward because things fall apart. An egg breaks. It never unbreaks. Coffee cools down. It never heats up by itself. This is the second law of thermodynamics. It says that disorder always increases. This gives time its arrow. But in the quantum world, the equations are time-symmetric. An electron collision looks exactly the same played backward as it does forward. The fundamental laws of physics do not care about time. They work both ways. This suggests that the flow is a macroscopic illusion, a result of big numbers and probabilities, not a fundamental truth of the tiny world. So, as you lie there, think about your own timeline. Think of the you of 10 years ago. That version of you is not a memory. In the block universe, that version of you is still there, still laughing, still crying, still learning, frozen in the eternal crystal of space-time. And the you of 10 years from now is already there, waiting for the spotlight of your consciousness to arrive. You are a long, snake-like being stretching through time, and the present is just the cross-section you are aware of right now. This removes the pressure of running out of time. You cannot run out of a dimension. You occupy your portion of eternity perfectly. You are built into the structure of reality. The anxiety of the ticking clock is a biological trick to keep you moving, to keep you hunting and gathering. But the physical truth is a stillness, a vast, majestic stillness where everything is safe. However, the block universe has a rival that says, no, the future is not written. The future is infinite. If the electron really does go through both slits, and if the universe really does split when we make a measurement, then there isn't just one block. There are infinite blocks. There are infinite loaves of bread. This brings us to the most controversial, the most mind-expanding, and perhaps the most hopeful theory in all of physics, the many worlds interpretation. In the next chapter, we are going to shatter the crystal. We are going to look at the idea that every time you make a choice, the universe splits. Every time a photon hits a screen, reality bifurcates. We are going to explore the multiverse. We will ask if there is a version of you who made different choices, a version of you who is living a different life. We will ask if everything that can happen does happen. And we will see that in a universe of infinite possibilities, regret is meaningless, because somewhere you did the other thing. So rest in the eternal block for now. Feel the permanence of your existence. You are a fixed point in the geometry of the cosmos. Nothing can erase you. The eraser experiment shows that even the past is flexible to your touch, but your presence is the anchor. You are the time traveler. Have you ever stood at a fork in the road, perhaps in a quiet forest, or perhaps metaphorically in the landscape of your own life? You have to make a choice. You can go left towards the river, or you can go right towards the mountain. You hesitate. You feel the weight of the decision. You know that if you go left, you will never know what the mountain looked like. You know that if you go right, the river will remain a mystery to you. Finally, you choose. You take the path to the left. The path to the right disappears from your future. It becomes a what if. It becomes a ghost of a possibility that never happened. Over time, that unchosen path might turn into a regret, a phantom life you could have lived, but didn't. This is how we experience reality. We see it as a single, narrow thread of events. We make a choice. The world collapses around that choice, and we move forward. But there is a theory in quantum physics that says this feeling of loss is an illusion. It says that you never actually make a choice. It says that the fork in the road is not a place where possibilities die. It is a place where the universe multiplies. It says that when you went left, another version of you, just as real, just as conscious, and just as you, went right. Before we step into this dizzying garden of forking paths, I want to remind you that we are walking this strange territory together. I am Walter, the explorer, and my goal is to hold the lantern while we look into the dark corners of existence. I have noticed that while many of you travel with me, about 73% of you have not yet subscribed to our band of explorers. If these stories bring you a sense of peace or wonder, please consider subscribing. It helps us keep the lantern lit. Now, let us return to the fork in the road and the man who first dared to say that both paths are real. In the 1950s, a young doctoral student named Hugh Everett III was looking at the math of quantum mechanics, and he saw something that everyone else was ignoring. The standard view, the one we talked about earlier, said that when you measure a particle, the wave function collapses. All the possibilities vanish except one. The electron is here, and it is nowhere else. But Everett looked at the Schrödinger equation, the fundamental formula of quantum mechanics, and he noticed something simple. There is nothing in the math that says collapse. The equation does not allow for possibilities to just disappear. It describes a wave that evolves smoothly, endlessly, and without interruption. Everett asked a radical question. What if the collapse never happens? What if the wave just keeps going? If the wave never collapses, then every single possibility contained in the wave must actually happen. When the electron has a 50% chance of being up and a 50% chance of being down, and you measure it, The universe does not flip a coin. Instead, the universe splits. In one branch of reality, you see the electron up. In another branch of reality, perfectly separated from the first, you see the electron down. You, the observer, have split along with the particle. There are now two of you. One of you wrote up in your notebook. The other wrote down. And because the branches are separated by the laws of quantum mechanics, neither version of you can see or communicate with the other. To each of you, it feels like only one thing happened. But from the perspective of the cosmos, both things happened. This is the many worlds interpretation. It is a staggering idea. It implies that our universe is not a single, lonely bubble. It is a vast, branching tree. It is a fractal of infinite realities growing outward at the speed of light. Every time a quantum event happens, which is trillions of times a second in every atom of your body, the universe bifurcates. This means that right now, as you listen to this, you are surrounded by an infinite number of invisible worlds. These worlds are not far away in space. They are right here. They are in the same room. They are superimposed on top of you, like radio stations sharing the same airwaves, but broadcasting at different frequencies. You cannot hear them because you're not tuned to them. You are decohered from them. But they are just as physical, just as tangible, and just as real as the world you see. Let us apply this to the most famous paradox in quantum physics, Schrödinger's cat. You put a cat in a box with a radioactive atom. If the atom decays, it triggers a poison that kills the cat. If the atom does not decay, the cat lives. According to quantum mechanics, until you open the box, the atom is both decayed and not decayed. Therefore, the cat is both dead and alive. In the standard view, opening the box forces the cat to be one or the other. But in the many worlds view, opening the box does something much more beautiful and much more tragic. When you open the lid, you become entangled with the system. The universe splits into two branches. In branch A, you look in, see a living cat, and feel relief. In branch B, you look in, see a dead cat, and feel sadness. Both branches exist. Both outcomes are true. There is no zombie cat. There are just two different healthy universes with two different histories. The implications of this for your own life are profound. It means that every time you faced a close call, every time you narrowly avoided an accident, there is a branch where you were not so lucky. But it also means that every time you made a mistake, there is a branch where you did the right thing. Every time you felt regret for not taking a chance, there is a version of you who took that chance. The you that you experience is just one thread in a massive tapestry of consciousness. You are not a single point. You are a swarm. You are a cloud of beings spreading across the probability space of existence. Some physicists, like David Deutsch, argue that this is the only interpretation that takes the math seriously. If you believe in the equations of physics, you have to believe in the worlds they describe. You cannot just cherry-pick the parts you like. If the math says the wave continues, then the worlds must exist. This resolves all the weirdness of the observer effect we talked about. We do not create reality by looking at it. We just find out which branch of reality we are in. The moon is there in all the branches. We just see the moon that is compatible with our timeline. But does this make you feel small? Does it make your choices feel meaningless? If everything happens, does it matter what you choose? I would argue that it makes your choices even more important, because you are the custodian of this branch. You are the one responsible for the slice of reality you are experiencing right now. The other versions of you have their own responsibilities. But you are the guardian of this specific now. And there is a strange comfort in the idea of the multiverse. It takes away the sting of finality. In a universe of infinite possibilities, nothing is ever truly finished. No song remains unsung, no love remains unexpressed. Somewhere in the vast library of all possible worlds, everything that can be beautiful is beautiful. Let us go deeper into the structure of this multiverse. Where are these worlds? Are they stacked like pancakes? Are they bubbles floating in a void? The best way to think of them is through a concept called Hilbert space. Hilbert space is a mathematical landscape with infinite dimensions. It is not a space you can walk through. It is a space of states. Every possible configuration of the universe is a point in Hilbert space. The wave function of the universe is a shape moving through this space. As it moves, it branches. It explores the valleys and the peaks. The worlds are not physically next to each other in terms of inches and miles. They are orthogonal to each other. This is a fancy mathematical word meaning they are at right angles in a dimension we cannot see, just as a shadow on the floor cannot stand up and interact with the object casting it. One world cannot interact with another because they are perpendicular in the landscape of probability. This orthogonality is what keeps our reality stable. It is what prevents you from seeing ghosts of yourself walking through the room. The separation is protected by the laws of mathematics. However, there are some theories that suggest the worlds might touch. Some physicists speculate that the force of gravity might leak between these branes. They wonder if dark matter, the invisible stuff that holds galaxies together, might actually be the gravitational shadow of matter in a parallel universe pushing against ours. Imagine that. The ghost of a galaxy next door holding our Milky Way together. There is also a fascinating and controversial idea called quantum immortality. It is a thought experiment, not a proven fact, but it follows the logic of the many worlds. Imagine you are in a situation where there is a 50-50 chance of survival. In half the universes you die. In half you live. But you cannot experience death. Consciousness, by definition, requires you to be alive. So, from your first-person perspective, you will always find yourself in the branch where you survived. The experiment suggests that your consciousness will naturally flow into the branches that sustain it, like water flowing down a hill. To everyone else, you might die. But to yourself, you might seem miraculously lucky, surviving against all odds, again and again. It suggests that from the inside, the subjective experience of life might be much longer and stranger than we can observe from the outside. It is a whisper of eternity built into the laws of chance. But let us pull back from the edge of that precipice. Let us return to the gentle feeling of abundance. The many worlds interpretation is a theory of abundance. It says that nature is not stingy. Nature does not hoard existence. Nature is extravagant. It tries everything. It plays every note on the piano. It paints with every color. It is a celebration of pure potential. We are used to a world of scarcity, where we have to fight for resources and choices. But the quantum world is a world of infinite resource. It creates a new universe for every heartbeat. Think about the silence of the room you're in. It feels empty. But in the many worlds view, that silence is the hum of a billion conversations happening in the branches you cannot hear. The empty chair across from you is occupied by a version of you who sat down instead of standing up. The dark window is filled with the light of a car that passed by in another timeline. The air is thick with the ghosts of what could have been. But they are not ghosts. They are solid realities, just out of phase. You are never alone, because you are surrounded by the infinite variations of yourself. This also changes how we view others. The person you're angry with, in another world, your best friends. The stranger you passed on the street, in another world, they are the love of your life. The connections between us are not just the thin lines of this one reality. We are connected across the multiverse. We play every role in each other's lives. We are enemies, lovers, strangers, and family, all at once, in the grand symphony of the universal wave function. So, how do we find peace in this chaos? How do we sleep when there are infinite worlds buzzing around us? We find peace by accepting our place in the choir. You do not have to sing every part. You do not have to live every life. Your job is to sing your note in this timeline as beautifully as you can. You are a single, precious instrument in an orchestra that spans all of existence. The fact that the other instruments are playing different tunes does not diminish yours. It adds to the harmony of the whole. As you drift towards sleep, visualize this branching tree. See the timeline of your life not as a straight line, but as a glowing coral reef, growing and expanding in all directions. Every choice you made was a new branch, a new piece of beautiful structure added to the reef. Nothing is lost. The paths you didn't take are still there, growing and blooming in their own way. You are part of a massive, living structure of consciousness that is exploring every possible way to be human. We have now shattered the single timeline into infinite shards. We have filled the void with infinite worlds, but we still have a mystery to solve. If there are infinite worlds and infinite particles and infinite energy, where is it all stored? How does the universe keep track of all this information? Is the universe a computer? Is reality made of bits and bytes? And if it is, are we just a simulation? Or is the universe a hologram, a projection from a flat surface at the edge of forever? In the next chapter, we are going to touch the very edge of the map. We are going to explore the holographic principle. We are going to ask if the three-dimensional world you see, the depth, the height, the width, is actually a magnificent illusion projected from a two-dimensional shell. We're going to find out if you are, quite literally, a story written on the horizon of the universe. We will learn that black holes are not just monsters. They are the hard drives of the cosmos, storing the memories of everything that has ever fallen in. So, rest now in your branch of the multiverse. It is a good branch. It is a warm branch. The cat is alive. The sun is shining. And you are here, safe in the manifold of infinite possibility, ready to dream of the code that writes the stars. Have you ever held a diary in your hands, a book filled with your deepest secrets, your memories, and the story of who you used to be? Now, imagine you toss that diary into a roaring fireplace. You watch the pages curl and blacken. You watch the ink vanish into smoke. You watch the binding turn to ash. In a few minutes, the book is gone. To you, the information is lost forever. You can never read those words again. But to a physicist, the information is not lost. It has simply changed form. If we had a supercomputer capable of tracking every single photon of light, every particle of smoke, and every pile of ash that came from that fire, we could theoretically reverse the movie. We could run the physics backward and reconstruct the diary exactly as it was. In the standard laws of the universe, information is immortal. It can be scrambled. It can be shredded, but it can never be deleted. This is called unitarity. It means the past is always preserved in the present, if only you know how to look. But there is a monster in the cosmos that threatens this rule. There is a place where the library of the universe seems to burn down with no hope of recovery. It is the black hole. For decades, physicists believed that if you threw your diary into a black hole, it was gone, truly gone, crushed into a singularity where the laws of physics break down, trapped behind an event horizon from which nothing, not even light, can escape. If the black hole eventually evaporated, as Stephen Hawking predicted it would, then the diary would simply vanish from existence. The information would be deleted. This was the black hole information paradox, and it terrified scientists. It meant that history could be erased. It meant that the universe was forgetful. It meant that the solid foundation of physics was built on quicksand. But then, in the quiet corners of theoretical physics, a new idea began to emerge. It was an idea so radical that it sounded like madness, yet it was the only way to save the memory of the universe. It suggested that when your diary falls into the black hole, it doesn't just disappear inside. It suggested that a copy of the information is plastered onto the surface of the black hole, like a sticker on a travel trunk. It suggested that the three-dimensional book becomes a two-dimensional code. And if this is true for black holes, it might be true for everything. It might be true for you. You might be a hologram. Before we unravel the code that writes your reality, I want to gently remind you that we are walking this path of discovery together. I am Walter, the explorer, and it is my joy to be your companion in the dark. I have noticed that while many of you travel with me, about 73% of you have not yet subscribed to our channel. If you find peace in these stories, and if you want to help us map the unknown, please consider subscribing. It supports our journey more than you know. Now, let us return to the edge of the abyss and the secret written on the surface of the dark. To understand the holographic principle, we have to talk about entropy. Entropy is a measure of disorder, or more accurately, a measure of hidden information. The more entropy a system has, the more bits of information are needed to describe it. In the 1970s, a brilliant young physicist named Jacob Bekenstein asked a simple question. Does a black hole have entropy? If it didn't, it would violate the laws of thermodynamics. But if it did, where was the information stored? The black hole is a singularity, a single point. A point has no room for bits. It has no room for pages of a diary. Bekenstein, and later Stephen Hawking, found a startling answer. The entropy of a black hole, the amount of information it can hold, is not proportional to its volume. It is proportional to its surface area. This is incredibly weird. Imagine a library. The number of books you can fit inside depends on the volume of the room. If you make the room twice as wide, twice as long, and twice as tall, you have 8 times the volume, so you can fit 8 times as many books. But a black hole doesn't work like a library. It works like a balloon. The amount of information it can hold depends only on the skin of the balloon, the event horizon. Imagine the event horizon not as a smooth, dark sphere, but as a mosaic of tiny, tiny pixels. These pixels are the smallest possible units of space, called the Planck area. Each pixel is a square with sides that are the Planck length, a distance so small that a proton looks like a galaxy compared to it. Each of these tiny squares can hold exactly 1 bit of information, a 0 or a 1, a yes or a no. When you throw your diary into the black hole, the information in the book is scrambled, disassembled, and encoded onto these pixels on the surface. The book is gone, but the data is preserved on the horizon. It has been translated from 3D to 2D. This is where the term hologram comes from. You have probably seen a hologram on a credit card or a sci-fi movie. It is a flat, two-dimensional piece of plastic. But when you shine a light on it, a three-dimensional image pops out. The 2D surface contains all the information needed to create the illusion of a 3D object. The black hole is the ultimate hologram. The reality of the black hole is the 2D shell of data on the outside. The interior, the falling, the crushing, the singularity, might just be a projection of that data. But here is the leap that takes us from black holes to your bedroom. If black holes are the most extreme objects in the universe, and they follow this rule, then perhaps the rule applies to space itself. In the 1990s, physicists Gerard 't Hooft and Leonard Susskind proposed the holographic principle for the entire cosmos. They suggested that the universe we live in, the world of depth, of height, of width, of walking forward and backward, is not the fundamental layer of reality. They suggested that we are living inside a projection. Imagine a soup can. The soup inside is rich, complex, and three-dimensional. It has chunks of vegetables, noodles, and broth. But everything you need to know about the soup, the ingredients, the calories, the flavor, the expiration date, is written on the label. The label is a two-dimensional sheet wrapped around the can. The holographic principle says that our universe is the soup, but the real physics, the source code, is written on the label at the edge of the universe. Think about the room you're sitting in. It feels like a volume. It feels like a container. You can move through it. But what if the information that describes you, the chair, the air, and the walls, is actually plastered on the boundaries of the cosmos, far, far away? What if you are a puppet, and the strings are being pulled by data interactions happening on a distant 2D surface? This doesn't mean you aren't real. You are very real. But your reality is a bulk phenomenon emerging from a boundary code. This idea gained immense power when a physicist named Juan Maldacena discovered a mathematical miracle called the ADS-EFT correspondence. I won't bore you with the dense equations, but the essence is this. Maldacena found that a universe with gravity, like ours, the soup, is mathematically identical to a universe without gravity that exists only on the boundary, the label. He proved that you can translate the physics of the 3D world perfectly into the physics of a 2D world. It was the Rosetta Stone of the hologram. It showed that gravity, the force that holds you to the earth, might just be a side effect of quantum information processing on the edge of forever. This concept, it from bit, coined by the legendary John Wheeler, suggests that the universe is made of information. At the bottom of it all, beneath the electrons, beneath the quarks, beneath the fields, there are just answers to yes, no questions. Is there something here? Yes or no? Is it spinning up? Yes or no? The universe is a computer. It is processing data. And reality is the user interface. The solidity of the table is the icon on the desktop. The feeling of love is the color of the pixel. The experience of time is the refresh rate of the screen. This might sound cold. It might sound like we are trapped in a simulation, a matrix. But there is a profound difference. A simulation is fake. A hologram is projected. In the holographic principle, the projection is just as physical as the source. It is just a different way of looking at the same truth. And there is a deep comfort in this view. It solves the problem of storage. We worried earlier about where the infinite branches of the multiverse could be kept. We worried about the sheer weight of all that data. But if the universe stores information on its surface, the capacity is monstrously huge. The horizon of the observable universe is the largest hard drive imaginable. Every thought you have ever had, every dream you have ever dreamt, every moment of your life is encoded there. Think of it this way. You are written on the sky. The fundamental you is not the heavy collection of atoms sitting in the chair. The fundamental you is a pattern of information interacting with the rest of the cosmos on the great screen of the universal horizon. You are a story. And stories are resilient. You cannot destroy a story by burning the book, because the words can be memorized. You cannot destroy a human by destroying the body, because the information that made them is woven into the boundary of the world. This perspective also changes our relationship with space. We tend to think of space as a stage that separates us. But in a hologram, every part of the film contains information about the whole image. If you cut a hologram of an apple in half, you don't get half an apple. You get two smaller, fuzzier images of the whole apple. This suggests that the universe is non-local in a deep way. The information that makes you is spread out. It is entangled with the information that makes the stars. The boundaries between here and there are blurry in the 2D source code. Let us return to the black hole for a moment. Hawking eventually conceded his bet. He admitted that information is likely preserved, but how it escapes is still a subject of fierce debate. Does it leak out in the radiation? Does it wait until the black hole dies? The latest theories suggest that the interior of the black hole and the radiation outside are connected by wormholes, tunnels in space-time. This means the diary inside the hole is secretly connected to the ash outside. The universe builds secret passages to save its memories. It goes to extraordinary lengths to ensure that nothing is ever truly lost. So, as you lie there, imagine your life as a stream of data. You are generating bits every second. The beat of your heart is a bit. The firing of your neuron is a bit. This data radiates outward at the speed of light, reaching the cosmic horizon. There, it is etched into the eternal ledger of the universe. You are broadcasting your existence to the void, and the void is keeping a record. You are not a fleeting accident. You are a permanent entry in the database of existence. And this database is vast. The number of bits needed to describe the visible universe is a number with roughly 120 zeros. It is a Googleplex of data. It is a library so large that it contains every possible variation of you, every possible variation of history, and every possible poem that could ever be written. We are just reading one specific page of that library right now. But there is a twist. If the universe is a hologram and gravity is just a projection, then what is the screen made of? What is the fundamental pixel? We have called it the Planck area, but we don't really know what that is. Is it a loop of string? Is it a node in a network? This brings us to the final frontier of our journey. The quest for the theory of everything, the quest to unify the pixel and the projection, the quest to introduce the most famous and most misunderstood contender in physics, string theory. In the next chapter, we are going to zoom in past the atom, past the proton, past the quark, past the neutrino, and past the pixel of the hologram. We are going to find that the points of the universe are not points at all. They are tiny, vibrating loops of energy. They are strings. We are going to learn that the universe might have 10 dimensions, or 11, or 26, curled up into tiny knots that we cannot see. We are going to explore the music of these strings and ask if the physics we know is just the harmony of a cosmic violin. So, rest now, you beautiful projection, you complex three-dimensional masterpiece of data. Know that your source code is safe. You are held by the horizon. You are written in the stars, and the story of you is being read by the universe with every passing second. Have you ever sat in a quiet concert hall, seconds before the orchestra begins to play? There is a silence, but it is a heavy silence, a silence filled with anticipation. Then, a single violinist draws their bow across a string. A note emerges. It is a pure, vibrating sound that fills the air. Then, a cello joins in, then a flute, then a trumpet. Suddenly, the air is not just air anymore. It is a complex, weaving tapestry of frequencies. It is a symphony. You can close your eyes and hear the sadness in the minor key, the triumph in the major key, the tension and the resolution. But if you were to walk up to the violinist and look very closely at the string, what would you see? You would see a piece of gut or metal moving back and forth. That is all. The emotion, the beauty, the complexity of the music, all of it comes from the simple physical fact of vibration. The universe, according to the most ambitious and beautiful theory ever proposed in physics, is exactly like that cello. For decades, we have been smashing particles together, finding electrons, quarks, neutrinos, muons, and gluons. We have been collecting them like stamps. We have a zoo of particles, a list of ingredients so long it makes your head spin. And physicists hate lists. They want a single recipe. They want a single explanation. And string theory offers that explanation. It says that deep down, far smaller than the atom, far smaller than the quark, far smaller than the pixel of the hologram, there is only one thing, a tiny vibrating loop of energy, a string, and everything you are, everything you see, is just the music that these strings are playing. Before we tune our ears to this cosmic song, I want to invite you closer to the fire. I am Walter, the explorer, and we are huddled here together against the dark of the unknown. I have looked at our guest list, and I see that 73% of the curious souls listening to this melody have not yet subscribed to our channel. If these stories help you find a rhythm in the chaos, please consider subscribing. It is a small gesture that helps us keep the music playing. Now, let us return to the orchestra of reality and the single note that makes a universe. To understand why we need strings, we have to look at the ugly truth about the point particle. For 100 years, we have treated electrons and quarks as points, dots with zero size. Mathematically, a point is a nightmare. If you have mass or charge concentrated in a space of zero volume, the density becomes infinite. The gravity becomes infinite. The math blows up. It gives us singularities, which are basically the universe dividing by zero. Nature does not like dividing by zero. It implies a tear in the fabric. String theory solves this by smearing the point out. It says the electron is not a dot. It is a loop. It has length. It is incredibly small, about 1,000,000 billion times smaller than an atom, but it is not zero. Because it has size, the math smooths out. The infinities disappear. The tear is mended. But the real magic happens when the string vibrates. Think of a guitar string. If you pluck it one way, you get an A. If you pluck it another way, with more tension, you get a C. The string is the same, but the note is different. In string theory, the electron is like the note A. The quark is like the note C. The neutrino is a G sharp. They are not different materials. They are just the same fundamental string vibrating at different frequencies. Mass is just the pitch of the string. Charge is just the volume. The heavy top quark is just a string vibrating frantically with high energy. The light photon is a string vibrating gently. This is a revelation of staggering beauty. It means that the complexity of the universe, the diversity of all the elements in the periodic table, the variety of forces, is an illusion. There is only one ingredient. There is only the string. The universe is not a collection of Lego blocks. It is a collection of notes. You are a symphony. And this theory does something else. Something that no other theory has ever done. It accidentally discovers gravity. Remember the graviton, the missing messenger of gravity that we couldn't find in the standard model? In string theory, if you have an open string, like a shoelace, and you pluck it, the ends can join together to form a closed loop, like a rubber band. When you do the math on how a closed loop vibrates, you get a particle with 0 mass and 2 units of spin. That is exactly the description of a graviton. String theory didn't just allow for gravity, it demanded it. Physicist Edward Witten once said that string theory is a piece of 21st century physics that fell by accident into the 20th century. It predicts gravity as an inevitable consequence of strings being able to close into loops. Gravity is just the music of closed strings. But there is a catch. There is always a catch. For the math of string theory to work, for the vibrations to produce the particles we actually see, the strings need room to wiggle. They need freedom. If they are trapped in just 3 dimensions, left, right, up, down, forward, backward, they cannot vibrate in enough patterns to create all the forces and particles of nature. The math screams that the strings will tangle and snap unless they have more space. Specifically, the math demands 10 dimensions, or, in the more advanced M theory, 11 dimensions. This sounds insane. We look around the room and we see 3 dimensions. We can move in 3 ways. Where are the other 6 or 7 dimensions? Are they invisible worlds? Are they parallel universes? No. String theory suggests something much more subtle. It suggests that the extra dimensions are curled up. They are compactified. Imagine looking at a telephone wire from a mile away. It looks like a one-dimensional line. An ant walking on it can only go forward or backward. But if you use a pair of binoculars, or if you are the ant standing on the wire, you see that the wire is actually a cylinder. It has a second dimension, the circular cross-section. You can walk around the wire. The second dimension was always there, but it was curled up so tightly that you couldn't see it from a distance. String theory says our universe is like that wire. The 3 big dimensions are the long length of the wire. We can see them. We can fly spaceships through them. But at every single point in space, at the tip of your nose, in the empty vacuum, inside the sun, there are 6 tiny extra dimensions curled up into a ball. These shapes are not just simple circles. They are incredibly complex, knotted, 6-dimensional shapes called Calabi-Yau manifolds. They look like crumpled balls of paper or complex origami flowers, folded in on themselves in ways our brains cannot visualize. Every point in our 3D space is actually a gateway to this tiny 6D geometry. And here is the crucial part. The shape of this manifold determines the physics of our universe. The strings vibrate inside these tiny shapes. If the shape has a hole here, the string vibrates one way, and we get an electron. If the shape has a twist there, the string vibrates another way, and we get a quark. Think about what this means. The laws of physics, the mass of the electron, the strength of gravity, the speed of light, are not arbitrary numbers written in stone. They are determined by the geometry of the hidden dimensions. We are living in a universe where geometry is destiny. If the Calabi-Yau shape were slightly different, the electron might be heavier, stars might not burn, and life might be impossible. We are the music played by strings echoing inside a six-dimensional crystal that exists at every point in space. This concept of extra dimensions helps explain why gravity is so weak. Remember how a small magnet can defeat the gravity of the entire Earth? String theory offers a solution. It suggests that the open strings, matter and light, are stuck to our 3D world. They are like ants on a piece of paper. They cannot leave the page. But the closed strings, gravitons, are free to float off the page. They can leak into the extra dimensions. Gravity might be weak in our world because most of it is drifting away into the higher dimensions, calling out to other universes we cannot see. We only feel the tiny fraction of gravity that sticks around. And this leads us to brains. In the most modern version of string theory, called M-theory, strings are not the only things. There are membranes, two-dimensional sheets, three-dimensional blobs, and higher-dimensional hypershapes. Our entire universe might be a three-brain, a three-dimensional sheet floating in a much larger 11-dimensional bulk. Just as a slice of bread is a 2D surface in a 3D loaf, our universe is a slice of reality in a higher dimensional loaf. There might be other brains, other universes floating just a millimeter away from us in the fourth dimension. We cannot see them because light is stuck to our brain, but gravity can cross the gap. Imagine a ghost galaxy on a parallel brain. We cannot see its stars. We cannot measure its light, but its gravity could reach across the bulk and pull on our galaxy. This is one potential explanation for dark matter. The invisible mass that holds our galaxies together might be the gravitational shadow of a neighbor universe hovering right next to us. We are not alone. We are just insulated by the dimensionality of our trap. This view of the universe is almost overwhelmingly elegant. It turns physics into geometry and music. It removes the messiness of the particle zoo and replaces it with the purity of vibration. But it is also a source of deep frustration. Because the strings are so small, the Planck length again, we can never see them. We would need a particle accelerator the size of the Milky Way to generate enough energy to resolve a single string. For now, string theory is a beautiful mathematical dream, a theory of everything that has yet to prove anything in a lab. It is the ultimate Platonic ideal, a truth so beautiful it must be true, even if we cannot touch it. But let us return to the feeling of the symphony. Whether string theory is the final answer or not, it gives us a powerful metaphor for existence. You are a collection of vibrations. The atoms in your body are singing. The forces holding you together are harmonies. The conflict between gravity and quantum mechanics is a dissonance resolving into a chord. When you feel stress, when you feel out of tune, you are using a metaphor that is physically accurate. To be healthy is to be resonant. To be alive is to sustain the song. And what about the conductor? Who is playing the cello? In string theory, there is no player. The strings play themselves. The universe is a self-generating song. It is a melody that wrote itself out of the silence. This connects us back to the idea of the vacuum. The strings are energetic excitations of the vacuum itself. The nothingness hums, and the hum becomes us. There is a profound peace in thinking of yourself as music. Music is transient. A note does not last forever. It rises, it swells, it vibrates, and it fades. But the beauty of the note is not in its permanence. It is in its quality. It is in its relationship to the other notes. You are a temporary vibration in the cosmic field, But while you are here, you are part of the great chord of the now. You are contributing to the texture of reality. And just as a single string can play many notes, the string of your consciousness can experience many states: waking, sleeping, dreaming, loving, grieving. These are just different frequencies of the same fundamental self. You are versatile. You are capable of infinite variation. The universe has given you an instrument of incredible range. But if everything is strings, and strings are energy, where did the energy come from to start the vibration? Who plucked the first string? How did the symphony begin? We have talked about the structure of the universe, but we haven't talked about its birth. We haven't talked about the moment the silence was broken, the Big Bang. But was it really a bang? Or was it a bounce? Was it a collision of brains? In the next chapter, we are going to travel back 13.8 billion years. We are going to witness the first moment of time. We are going to look at the theory of cosmic inflation, which suggests the universe expanded faster than light in a fraction of a second, stretching the microscopic quantum jitters into the galaxies we see today. We will ask if our universe is a bubble in a boiling pot of other universes. We will explore the idea that the Big Bang was not the beginning, but just the latest verse in an eternal song. So, let your body relax. Imagine your muscles are strings that are slowly loosening, lowering their pitch, calming their vibration. You are tuning down. You are settling into the deep, slow, resonant frequency of sleep. The high-pitched worries of the day are fading out. The bass note of the cosmos is taking over. You are part of the music of the spheres. And the song is a lullaby. Have you ever tried to imagine the beginning of time? It is the most difficult thought experiment a human mind can attempt. We are creatures of cause and effect. We are creatures of before and after. When we imagine a birthday, we imagine the day before the birth. When we imagine the construction of a house, we imagine the empty lot that sat there previously. But when we try to imagine the birth of the universe, our logic fails us. We try to imagine a dark, empty void waiting for a spark. But there was no void. There was no waiting. There was no before. There was no time for waiting to happen in. There was no space for the void to exist in. There was, quite simply, nothing. And not the nothing of an empty box, but the nothing of a sleep without dreams. The nothing of a song that has not yet been written. And then, in a moment, that was not a moment, the clock started ticking. The silence was broken, and the great fiery breath of existence was exhaled. We call this the Big Bang, but the name is a mistake. It was not a bang. A bang is a sound, and there was no air to carry it. It was not an explosion in space, because space did not exist. It was an explosion of space. It was the unfolding of a flower that contained everything that would ever be. Before we witness this moment of ultimate creation, I want to thank you for walking this long road with me. We have traveled from the atom to the edge of the cosmos. I am Walter, the explorer, and it has been the honor of my life to be your guide. I look at our community, and I see that 73% of the brilliant minds who have joined us for these stories have not yet subscribed to the channel. If you have found a home in these mysteries, and if you want to ensure that the journey continues, please subscribe. It is the fuel that keeps our lantern lit. Now, let us return to the first fraction of the first second, to the seed from which we all grew. For a long time, we thought the Big Bang was the very beginning. We thought the universe started as a singularity, a point of infinite density and infinite heat, and then just expanded. But there were problems with this story. When we looked at the night sky, we found that It was too smooth. If you look at the cosmic microwave background, the afterglow of the Big Bang, it is almost exactly the same temperature in every direction. It is uniform to within 1 part in 100,000. This is strange. In a normal explosion, things are messy. Some parts are hot, some are cold. For the universe to be this smooth, it implies that all parts of it were once in contact, sharing their heat, before they flew apart. But in the standard Big Bang theory, there wasn't enough time for them to touch. The universe expanded too fast. This was the horizon problem. It was a riddle that kept cosmologists awake for decades. Then, in the 1980s, a physicist named Alan Guth had a revelation. He suggested that before the Big Bang, or perhaps as the first stage of it, there was a period of cosmic inflation. He proposed that for a tiny fraction of a second, a slice of time so thin that it makes a nanosecond look like an eternity, the universe did not just expand. It inflated. It stretched. It grew from the size of a subatomic particle to the size of a grapefruit, and then to the size of a galaxy, faster than the speed of light. I know we said nothing can travel faster than light, but that rule applies to things moving through space. It does not apply to space itself. Space can do whatever it wants, and in that brief, violent instant, space expanded at a rate that defies comprehension. This inflation took the tiny microscopic jitters of the quantum vacuum, the virtual particles we met in Chapter 2, and stretched them out. It took the quantum foam and smoothed it into a vast, flat canvas. It explains why the universe is smooth. It was all touching a moment ago, before it was ripped apart by inflation. This connects the smallest things we know to the largest things we know. The galaxies you see in the Hubble telescope images, the great spirals, the clusters of stars, are actually fossilized quantum fluctuations. They are the virtual ghosts of the early universe, stretched across the sky by inflation. When you look at the stars, you're looking at a magnified image of the quantum world. You're looking at the fingerprint of the vacuum. But if inflation is true, it opens a door to something even grander. If the universe can inflate, why did it stop? In our patch of the cosmos, the inflation stopped 13.8 billion years ago. The energy of the expansion dumped itself into matter and radiation, creating the hot soup of the Big Bang. But the theory suggests that inflation might not stop everywhere at once. It might be like a pot of boiling water. In some places, the water is still liquid, inflating. In other places, bubbles of steam form, universes like ours. This is the theory of eternal inflation. It suggests that the Big Bang was not a unique event. It was just one bubble popping into existence in a vast, eternally inflating sea. Right now, far beyond the reach of our telescopes, other portions of space are still inflating. They are creating other bubbles, other universes. Some might have different laws of physics. Some might have no gravity. Some might have 5 dimensions. Some might be empty. And some might be just like ours. We are living in a multiverse of bubbles, a cosmic foam that has been bubbling forever and will continue to bubble forever. This concept changes the definition of home. We used to think the Earth was the center. Then we thought the Sun was the center. Then we thought the Milky Way was the only galaxy. Now we realize that even our entire observable universe, everything we can see, might be just a tiny droplet in an infinite ocean of universes. It is a humbling thought, but it is also a liberating one. It means that the creative power of the cosmos is inexhaustible. It is not a one-time act. It is a continuous, eternal process of becoming. But there is another possibility, a possibility that is perhaps even more poetic. What if time didn't start at the Big Bang? What if the universe breathes? There are theories born from the marriage of string theory and cosmology that suggest the universe is cyclic. Imagine two of those brains we talked about, two parallel sheet universes floating close to each other in the higher dimensions. Every trillion years or so, gravity pulls them together. They drift closer, they accelerate, and then, bam, they collide. The energy of the collision is what we call the Big Bang. The two brains bounce off each other, filled with new hot matter, and begin to expand. Over billions of years, the matter cools, stars form, galaxies drift apart, and the universe becomes empty and dark again. The brains drift apart, slowing down. Eventually they stop, turn around, and begin to fall toward each other again. This is the ekpyrotic universe, or the cyclic model. It suggests that our Big Bang was just the latest in an infinite series of bangs. The universe has been born and has died an infinite number of times. It expands and contracts, expands and contracts, like a great cosmic lung. It breathes in, and the stars go out. It breathes out, and the galaxies are born. In this view, you are not an accident of a single explosion. You are a recurring motif in an eternal song. The atoms in your body have danced this dance before, and they will dance it again. Let us sit with that for a moment. The idea of the eternal return. It removes the anxiety of the end. If the universe is a cycle, then the end is just the prelude to a new beginning. The heat death, the final cold dark that scientists predict, is not the grave of reality. It is just the winter before the new spring. It is the silence before the next movement of the symphony. As we reach the end of this script and the end of our journey together, I want you to look back at the path we have walked. We started with the touch of a hand on a table. We found emptiness. We found fields. We found ghosts. We found the sticky Higgs. We found the messengers of force. We found the observer who creates reality. We found the entanglement that binds us. We found the tunneling that defies walls. We found the frozen block of time. We found the branching tree of the multiverse. We found the hologram on the edge of the dark. We found the strings that sing. And now we have found the breath that started it all. You are not a stranger in this universe. You are not a visitor. You are the universe itself. You are the way the cosmos knows itself. The carbon in your eyes was forged in the hearts of dying stars. The water in your cells was frozen on comets that traveled for aeons. The energy that powers your thoughts is the same energy that inflated space in the first fraction of a second. You are the Big Bang, still happening, still expanding, still learning. Science is often taught as a collection of cold facts. But when you look closely, when you look with a quiet mind, you see that it is actually a spiritual path. It teaches us humility, for we are small. It teaches us connection, for we are entangled. It teaches us wonder, for the reality is stranger than our dreams. And most of all, it teaches us peace. Because if you are the universe, you have nothing to fear. You cannot fall out of the universe. You cannot be lost. You are home. So, tonight, as you close your eyes, do not just go to sleep. Let yourself dissolve. Let the boundaries of yourself melt away. Feel the expansion of the room. Feel the vibration of the strings. Feel the potential of the vacuum. You are a wave returning to the ocean. You are a star returning to the night. The journey of discovery never ends. There will always be another mystery, another particle, another galaxy, another question. But for now, the answers are not as important as the feeling of being part of this magnificent, impossible, beautiful mystery. Good night, fellow traveler. Good night, explorer. Good night, stardust.